For a long time, we have looked at the night sky as observers. We saw the universe as something separate from us, a story happening on a scale so large that we could only watch. The universe expands, galaxies move apart, and we are carried along with it. But what if that is not the whole story? Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. What if life, this quiet and complex process, is not just a passenger in the cosmos? What if it has a role to play in how the universe behaves? This is a journey into a quiet, and sometimes difficult, idea in science. An idea that touches on the nature of physical law and our place within it. It is an exploration of a possibility that our existence might have some small influence on the shape of space and time. A universe in motion, the discovery of cosmic expansion. To begin asking a question like this, we need to go back to a time when our picture of the cosmos was much smaller. In the 1920s, the common view was that our own galaxy, the Milky Way, was the entire universe. It was seen as an island of stars in an otherwise empty space. Other hazy patches of light, called spiral nebulae, were thought to be clouds of gas inside our own galaxy. Atop Mount Wilson in California, an astronomer named Edwin Hubble was looking at these nebulae through the largest telescope in the world. He was looking closely at one of them, the Andromeda Nebula. Inside it, he found a particular kind of star known as a Cepheid variable. These stars are useful. They brighten and dim with a steady rhythm, and the speed of that rhythm is directly connected to the star's true brightness. This had been discovered by another astronomer, Henrietta Swan-Leavitt. By comparing how bright a Cepheid star truly was to how dim it appeared from Earth, Hubble could work out how far away it was. His measurements began to change the old picture of the universe. The star in Andromeda was almost 1,000,000 light-years away, far outside the Milky Way. This meant Andromeda was not a cloud of gas. It was another galaxy, a city of stars much like our own. The known universe suddenly grew much larger, filled with countless other island universes. But Hubble's next discovery was even more important. He began to study the light coming from these distant galaxies. When light is split into its colors, it creates a spectrum. Hubble noticed that the light from nearly every galaxy was stretched, its spectrum shifted toward the red end. He had found cosmological redshift. This is similar to the Doppler effect, where the sound of an ambulance siren becomes lower in pitch as it moves away. A galaxy that is red-shifted is a galaxy moving away from us. Hubble saw a simple pattern. The farther away a galaxy was, the faster it was moving away. This became known as Hubble's law, and it was the first real evidence that the universe is expanding. It is important to be clear about what this expansion means. The galaxies are not moving through space like pieces of an explosion. Instead, the fabric of space itself is stretching. A common way to picture this is to think of a loaf of raisin bread rising in an oven. The raisins are the galaxies, and the dough is space. As the dough expands, every raisin moves away from every other raisin. From the perspective of any one raisin, all the others seem to be moving away, and the farthest ones seem to move fastest because there is more expanding dough between them. This is our universe. It does not have a center or an edge. From here in the Milky Way, it looks like everything is moving away from us. But an observer in any other galaxy would see the same thing. This was not an explosion in space, it was the expansion of space. It began 13.8 billion years ago from a hot, dense state we call the Big Bang, and it has been expanding and cooling ever since. For the first few billion years, this expansion was a contest between two forces. The outward expansion pushed everything apart, while gravity pulled everything together. For a long time, gravity was winning, and the expansion was slowly getting slower. But then, something changed. The cosmic accelerator and a new cosmic mystery. Around 1998, two teams of astronomers were trying to measure exactly how much the universe's expansion was slowing down. They used a specific kind of stellar explosion, a type Ia supernova. These explosions are useful because they all have nearly the same true brightness, so they can be used to measure very large distances. The idea was simple. Look at very distant supernovae to see how fast the universe was expanding long ago, and compare that to how fast it is expanding now. The expectation was clear. The distant supernovae should look brighter than expected, which would mean that gravity had slowed down the expansion in the billions of years since their light began its journey. But that is not what they found. The distant supernovae were dimmer than they should have been. They were farther away than the old models predicted. The only way to explain this was if the expansion of the universe had stopped slowing down, and had started to speed up. This discovery was so unexpected it led to the 2011 Nobel Prize in Physics. It was as if you had thrown a ball into the air and, instead of falling back down, it had suddenly started moving upward, faster and faster. Physics had a new, quiet mystery to solve. What was this invisible influence, pushing the universe apart against the pull of gravity? Scientists gave it a name that reflected how little was known about it: dark energy. This acceleration did not happen right away. For the first 9 billion years or so, gravity was stronger, and the expansion did slow down. But about 4 to 5 billion years ago, as the universe grew larger and matter spread out, the effect of dark energy became dominant. Since then, it has been the main force shaping the cosmos on its largest scales, pushing galaxies apart at an increasing speed. Today, it is thought to make up about 70% of everything in the universe. For a long time, this story seemed complete. We lived in an accelerating universe that would end in a big freeze, with galaxies so far apart they would disappear from each other's view, leaving behind a cold, empty space. But our understanding of the universe is always changing. In the last couple of years, new data has appeared. Analyses from large sky surveys and new looks at the supernova data have hinted at something different. Some studies now suggest that dark energy might not be constant. It might be weakening over time. One study, for example, from Yonsei University, corrected the supernova data for the age of the galaxies they were in. It found evidence that the universe might have already entered a new phase of slowing down. This is a significant change from the standard model. If these findings are confirmed, it could mean our universe is not heading for a big freeze, but perhaps a big crunch, where a weaker dark energy allows gravity to pull everything back together billions of years from now. These results are new and still being debated. They challenge what has been the standard view for more than 20 years. But they show that our understanding of what drives the universe is still incomplete. The nature of dark energy is one of the biggest unanswered questions in physics. Is it a fixed property of space itself? Or is it something that changes over time? This uncertainty about the rules of the cosmos opens the door to even quieter, deeper questions. If the rules can change, what sets them in the first place? And this leads to another cosmic coincidence: the fine-tuning problem. A universe just right for life. Have you ever wondered, in a quiet moment, why we exist in a physical sense? The fact that you are here, able to think and to breathe, is the result of a series of what appear to be strange coincidences. The laws and constants of physics seem to be balanced with an incredible precision, a precision that allows stars, planets, chemistry, and eventually, life to exist. This is often called the fine-tuning problem. Consider a few examples. Think of gravity. It is strong enough to form stars and galaxies, but weak enough that stars do not burn out too quickly or collapse before life can form on planets around them. If the strength of gravity were changed by just 1 part in 10 to the power of 60, the universe would have collapsed on itself just after the Big Bang. There would be no stars, no galaxies, and no us. Or consider the cosmological constant, the number that represents the density of dark energy. The value we observe is very small. If it were much larger, space would have expanded so fast that atoms and galaxies would never have formed. If it were negative and only slightly larger, the universe would have collapsed immediately. The observed value is precise to about 1 part in 10 to the power of 120. It's a precision so fine it is difficult to describe. The list continues. The strong nuclear force, which holds atoms together, is also just right. If it were a little weaker, only hydrogen would exist. No carbon, no oxygen, no complex chemistry. If it were a little stronger, all the hydrogen would have been used up in the Big Bang, leaving no fuel for stars like our Sun. The mass of a neutron is just slightly more than the mass of a proton. This allows some neutrons to turn into protons, creating a universe with a lot of hydrogen. If the proton were just a tiny bit heavier, it would decay into neutrons, and atoms as we know them would not exist. It is a cosmic puzzle. Everything seems to be just right. The universe is not too fast, not too slow, not too simple, not too chaotic. It appears, against very long odds, to be arranged in a way that allows for our existence. How do we explain this? Is it just an accident? Or is there something else going on? This question brings science to its edge, to a place that touches on philosophy. The anthropic principle: is the universe for us? In the face of this fine-tuning, scientists have considered a quiet and sometimes controversial idea: the anthropic principle. In its simplest form, the weak anthropic principle is an observation about perspective. It says that we observe the universe to have these finely tuned properties simply because if it did not, we would not be here to observe it. It is like asking why we find ourselves on a planet with liquid water and a breathable atmosphere. Creatures like us, who need water and oxygen, can only evolve on such a planet. We should not be surprised to find our environment suited to our existence, because we are a product of it. In the same way, we can only find ourselves in a universe with laws that allow for observers to exist. Any other kind of universe would be empty of anyone to see it. While this is logical, some find it unsatisfying. It explains that the constants must be this way for us to be here, but not why they are this way. This feeling of dissatisfaction led to the strong anthropic principle. This idea suggests that the universe was, in some way, required to have properties that would eventually allow for intelligent life to emerge. This idea comes in several forms. Some see it as evidence of a creator. Others have turned to a different explanation: the multiverse. The multiverse idea suggests that our universe is just one of many, perhaps an infinite number of universes, each with its own randomly set physical laws. In this scenario, it is no longer surprising that at least one universe, ours, would have the right conditions for life. We are simply living in one of the universes where it was possible. The other universes are unobserved because they are sterile and empty. The multiverse offers a possible explanation for fine-tuning without needing a creator or incredible luck. But it has a significant problem. It is very difficult, and perhaps impossible, to test. If these other universes are disconnected from our own, we may never be able to prove they exist. This leads some to say it is not science. But what if there is a third option? One that does not depend on unseen universes or a supernatural designer. What if the connection between life and the universe is not a coincidence to be explained, but a basic feature of reality itself? What if life is not the result of the universe's properties, but somehow part of the cause? The speculative leap. Life as a cosmic architect. Here we move to the edge of current thinking, to ideas that are not part of mainstream science, but are being discussed. What if the relationship between life and the universe is not a one-way street? One of these new ideas is called *assembly theory. Developed by chemist Lee Cronin and his colleagues, It offers a way to measure the complexity of an object by counting the minimum number of steps needed to make it from basic parts. A simple molecule has a low assembly index. A complex molecule, like DNA, has a very high one. The important insight is this. While simple objects can form by chance, very complex objects almost never do. If you find many copies of a highly complex object, like a living cell, it is a sign that it was not an accident. It is a sign that a process of selection and memory was involved. In other words, it is a signature of life. This idea tries to build a bridge between physics and biology. Evolution is seen as a process that remembers how to build complex things. How could this connect to the universe? The theory speculates that the universe itself might be a system that evolves toward complexity. Perhaps the laws of physics are not fixed, but are more like rules that allow new, complex things like life to appear. And perhaps, through some process we do not yet understand, life's ability to create complexity over time feeds back into the cosmic system. This has echoes of another speculative idea from the 1990s, called cosmological natural selection proposed by physicist Lee Smolin. Smolin's idea is a kind of cosmic evolution. He suggested that every time a black hole forms, it might create a new, baby universe, with slightly different physical constants. In this model, natural selection would apply to universes. Universes with constants that are better at making black holes would have more offspring. Over many generations, the most common universes would be the ones that are very good at making black holes. And a universe that is good at making black holes, by making large stars, turns out to look very similar to a universe that is good at supporting life. In this view, the fine-tuning is not for us. It is for making black holes, and we are just a side effect of a universe that has evolved to reproduce itself. Both of these ideas are speculative. They are not proven, but they represent a different way of thinking. They suggest that concepts from biology, like evolution and selection, might apply on a cosmic scale. They hint that the universe might not be a static stage, but a dynamic system where life is an important actor. The sobering reality check and the unshakable mystery. It is a compelling vision, life having a role in shaping the cosmos. But now we must return to what we can observe. As of today, is there any direct evidence that life influences the expansion of the universe? The answer is no. Cosmology deals with immense scales. The equations that describe the universe are governed by the density of matter, radiation, and dark energy. In this accounting, all of the life we know of is a whisper. The total mass of all life on Earth is incredibly small compared to the mass of the Earth itself, which is incredibly small compared to the Sun, which is just one of hundreds of billions of stars in our galaxy. The expansion of space happens between clusters of galaxies. It does not happen inside your body, or inside the Earth, or even inside the Milky Way. In these places, gravity has already won. Measurements from our best telescopes show a universe that is very uniform on large scales. The expansion seems to be the same in every direction, governed by physical laws that show no sign of being influenced by the quiet chemistry happening on a few small planets. Life seems to ride along with cosmic expansion, it does not steer it. We are also left with the Hubble tension. This is a quiet but persistent disagreement between our two main ways of measuring the universe's expansion rate. When we measure it using nearby stars and supernovae, we get a value of around 73 km per second per megaparsec. But when we measure it using light left over from the Big Bang, we get a value of around 67. For years, it was thought that better measurements would resolve this difference. Instead, the disagreement has become more certain. It suggests that there may be something missing from our model of the universe. Perhaps there is a new particle, or dark energy behaves in a more complex way than we thought. But no proposed solution involves biology. So we are left with a quiet contradiction. On one hand, All evidence points to a universe indifferent to life, governed by the cold mathematics of physics. On the other hand, we have a universe that seems impossibly fine-tuned for life to exist. We have journeyed from the known to the speculative, from the expanding universe to the quiet edges of cosmic evolution. The idea that life might shape the cosmos is one of the deepest questions we can ask. It touches the boundary between physics and biology, between the observer and the observed. What are your thoughts on this? Is the universe a coincidence, a sign of something more, or a hint that life has a role we do not yet understand? Feel free to share where you're watching or listening from, and any thoughts you have. The story of the universe has been one of expanding horizons. We once thought the Earth was the center of everything. Then it became a planet around a star. Then our star became one of billions in a galaxy, and our galaxy one of trillions in an expanding cosmos. At each step, our place seemed to become less significant. And yet, the mystery of fine-tuning brings us back to a startling thought. The anthropic principle suggests our existence is significant. The speculative ideas of cosmic evolution go further, hinting that the emergence of life might not be an accident, but a central part of the cosmic story. As of today, these remain ideas on the frontier. The data we have tells us that expansion is governed by matter and dark energy. But the fact that we do not understand dark energy, or why its value is so precise, reminds us how much we still have to learn. The recent hints that cosmic acceleration might be slowing only add to the mystery. We live in a universe that is whispering secrets. We hear them in the light from distant galaxies, in the flicker of dying stars, and in the fundamental constants that define our reality. For now, the idea that life influences the expansion of the universe is a quiet speculation. But perhaps we are not just stardust. Perhaps we are the universe's way of thinking about itself. And perhaps the act of observing, of learning, and of becoming complex is a quiet force of its own, with a role to play on a scale we are only just beginning to imagine. The question remains, waiting patiently for understanding to catch up. The universe is expanding wrong and scientists are worried. There is a number, just one number that seems to dictate the past, present, and future of everything we see. It governs the scale of the cosmos, the age of the stars, and the ultimate fate of reality itself. For decades, we thought we had it understood. We built our entire model of the universe on it. But there is a problem. A quiet, persistent problem. The number appears to be wrong. Or rather, we have two numbers. Two of our most trusted, most precise ways of measuring the growth of the universe are giving us two different answers. This is not a small rounding error. It is a crack running through the foundations of physics. This isn't just a disagreement between astronomers. It is a cosmic crisis. A tension, as they calmly call it, that could force us to rewrite what we thought we knew about space, time, and our place within it all. Some have even begun to wonder if this cosmic glitch might be connected, in the strangest and most profound way, to the emergence of life itself. Imagine you are trying to measure how fast a car is moving. Your radar gun says it's going 67 miles per hour. But your speedometer, which you also trust, is locked in at 73. You check them again and again. The numbers don't change. Is one of your tools broken? Or is something fundamentally strange happening with the car itself? Something that seems to defy the known laws of motion? This is the situation astronomers find themselves in. They are standing on the side of the cosmic highway, and their measurements for the universe's expansion do not add up. This discrepancy is what they call the Hubble tension, and it has become one of the most fundamental questions in all of science. To understand this crisis, we first need to understand the number at its heart, the Hubble constant, written as h0. Let's start with a simple, classic way to picture it. Imagine a loaf of raisin bread dough, rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, it looks like all the others are rushing away from it. The farther away a raisin is, the faster it seems to recede, because there's more expanding dough between them. In the 1920s, the astronomer Edwin Hubble discovered that our universe works just like this. Galaxies are not just flying through a static, empty void. The fabric of space itself is stretching, carrying galaxies along for the ride. He found a clear relationship. The farther away a galaxy is, the faster it's moving away from us. This is not because we're at the center of some great explosion. An observer in any galaxy would see the same thing. The Hubble constant, h0, is the number that quantifies this expansion. It's measured in a unit that sounds a little strange at first: kilometers per second per megaparsec. A megaparsec is simply a unit of distance, an enormous one, equal to about 3.26 million light-years. So, if h0 is, say, 70 kilometers per second per megaparsec, it means that for every 3.26 million light-years you look further into space, galaxies are receding 70 kilometers per second faster. A galaxy 1 megaparsec away would be moving away at 70 kilometers per second. A galaxy 2 megaparsecs away would be receding at 140 kilometers per second. 10 megaparsecs away, 700 kilometers per second. It is a fundamental scaling factor for the entire cosmos. This number is incredibly important for two main reasons. First, it tells us the scale of the universe. If you can measure how fast a galaxy is moving away, you can use the Hubble constant to calculate its distance. Second, and perhaps more profoundly, you can run the cosmic clock backward. If you know how fast things are moving apart, you can calculate how long it took for them to get where they are today, all the way back to the Big Bang. The Hubble constant, therefore, gives us the age of the universe. A larger h0 means a faster expansion and a younger universe. A smaller h0 means a slower expansion and an older one. Understanding this number is fundamental to our entire cosmic story. The argument over the universe's expansion rate is nothing new. It is a quiet drama that has been playing out for nearly a century. When Edwin Hubble first proposed his constant in 1929, his initial estimate was a staggering 500 kilometers per second per megaparsec. This created an immediate problem. A number that high suggested the universe was only about 2 billion years old. Geologists, however, had already dated Earth's rocks to be much older. The universe could not be younger than its own planets. This began a decades-long debate. In one corner was Alan Sandage, Hubble's own student, who argued for a much smaller number, around 50, which would make the universe comfortably older. In the other was Gerard de Vaucouleurs, who consistently measured a much higher value, closer to 100. For years, the community was split, with each side defending their numbers. To an outsider, it looked like astronomers couldn't agree on the most basic property of the cosmos. The stalemate was finally broken by a new eye in the sky, the Hubble Space Telescope. One of its main goals was to settle this very debate. By observing special pulsing stars called Cepheid variables in distant galaxies with new clarity, it could make far more accurate distance measurements than ever before. In 2001, a decade-long project delivered its answer, concluding the value was around 72. For a time, it seemed a kind of peace had been restored. Most astronomers settled on a value near 73, which gave our universe a respectable age of about 13.8 billion years. The great debate appeared to be over. But this peace, it turned out, was built on a foundation that was about to show its first crack. The problem we face today is more subtle, but also more profound. It is not a fight between two astronomers, but between two completely different ways of looking at the universe, studying its childhood and studying its adulthood. And they are telling us two different stories. The first method looks back in time, to the universe's baby picture. This picture is the cosmic microwave background, or CMB. It's the faint, residual glow of heat left over from the Big Bang, from when the universe was just 380,000 years old. Before this, the universe was an opaque soup of particles and radiation. As it cooled, atoms formed, and the universe suddenly became transparent. The light from that moment has been traveling across the cosmos ever since. This isn't just a uniform glow. It has tiny temperature fluctuations, which mark the seeds of all future structure. These are the ripples in the primordial soup that would eventually grow into galaxies, stars, and us. Satellites like the European Space Agency's Planck mission have mapped these ripples with breathtaking precision. By studying their size, physicists can use our best model of the universe, the lambda-CDM model, to predict how the universe should have evolved. It is not a direct measurement of today's expansion. It is a prediction, based on the universe's starting conditions. The answer it gives is consistently around **67 km per second per megaparsec. The second method doesn't rely on predictions from the past. It measures the expansion rate directly, in the late universe we see around us today. The primary technique is called the cosmic distance ladder. The first rung is simple geometry. Astronomers measure how nearby stars appear to shift against a distant background as the Earth orbits the Sun. This technique, called parallax, works only for stars within our own galaxy. The next rung relies on Cepheid variables. These are pulsating stars whose brightness is linked to their pulsation period. If you know a star's true brightness and measure how bright it appears, you can calculate its distance. To reach even farther, astronomers use Type Ia supernovae. These are spectacular explosions that are remarkably consistent in their peak brightness. They are so brilliant they can outshine their entire host galaxy, allowing us to see them billions of light-years away. By calibrating each rung with the one before it, astronomers build a robust map of the universe's expansion. The leading team doing this work, led by Nobel laureate Adam Rees, has refined this measurement for years. Their latest results, sharpened by the James Webb Space Telescope, have only deepened the mystery. JWST confirmed the earlier measurements were not in error. The disagreement was real. Their value is **73 km per second per megaparsec. So here is the crisis. The early universe predicts 67. The late universe measures 73. The margins of error do not overlap. This is a 5 sigma discrepancy, a statistical term meaning the chance of it being a random fluke is about 1 in 3.5 million. Other independent methods, like using the light from distant quasars bent by gravity, also tend to point toward the higher value. It feels as if the universe had a calm, predictable childhood that grew up into a surprisingly fast-paced adult. The bridge between them, our standard model of cosmology, appears to be broken. The persistence of this tension is forcing physicists to confront a startling possibility. Our best model of the universe might be incomplete. If both measurements are correct, then something new must be happening in the 13.8 billion years that separate them. Here are some of the possibilities being explored. One idea is that dark energy, the mysterious force causing expansion to accelerate, is not constant. Perhaps there was a burst of early dark energy in the young universe. This would have given the cosmos an extra push that faded over time, changing the expansion history in a way that could reconcile the two measurements. Another possibility is that the universe is hiding new, undiscovered particles. A popular candidate is a sterile neutrino, a fourth type of neutrino that interacts only through gravity. These extra, fast-moving particles in the early universe would be a form of dark radiation, which could alter the cosmic expansion just enough to resolve the tension. This is the most radical idea. What if our understanding of gravity itself is incomplete? Einstein's theory of general relativity has passed every test we've thrown at it, but mostly within our solar system. Perhaps on the very largest cosmic scales, gravity behaves differently. This is a fringe idea, But the stubbornness of the tension is making scientists consider even the most dramatic possibilities. Any of these solutions would mean our picture of the cosmos, with just 5% normal matter, 27% dark matter, and 68% dark energy, is missing a crucial piece. The Hubble drama is about the asterisk rate of expansion, but it's linked to another fundamental question. What is the asterisk scale of the universe? First, there is the asterisk observable universe. This is the portion of the cosmos from which light has had time to reach us. The universe is about 13.8 billion years old, so you might think the observable universe is 13.8 billion light-years in radius. But this ignores a crucial fact. Space has been expanding the entire time that light has been traveling. Imagine a firefly emits a flash of light 13.8 billion years ago. As that photon of light travels toward us, the space it is traveling through is stretching. So, the firefly itself is now much, much farther away. When we calculate how far away the object that emitted the oldest light we can see is today, the answer is a mind-boggling asterisk 46.5 billion light-years. This makes the diameter of our observable universe about asterisk 93 billion light-years. This is our cosmic bubble. But is that the asterisk entire universe? Almost certainly not. There is no reason to believe that the universe just stops at the edge of what we can see. The honest answer is, we don't know how big the whole thing is. It might be infinite. Our best measurements show that space is almost perfectly flat. If it is perfectly flat, then like a flat sheet of paper, it likely goes on forever. Some estimates suggest the total universe is at least 250 times larger than our observable sphere. We are like a single bacterium in the Pacific Ocean, trying to comprehend the whole planet. Our story of cosmic expansion has one more dramatic turn. For most of the 20th century, astronomers assumed the universe's expansion must be slowing down. Gravity pulls things together, so it should be acting as a brake. The only question was if it would slow down forever or eventually stop and collapse. It was a logical assumption. And it was wrong. In 1998, two independent teams set out to measure this deceleration using Type Ia supernovae. They both found the exact opposite of what they were looking for. The most distant supernovae were dimmer than expected. There was only one plausible explanation. They were farther away than they should have been. The expansion of the universe was not slowing down. It was speeding up. This discovery, which won the Nobel Prize, meant some mysterious, repulsive force was woven into the fabric of space itself, pushing everything apart. This invisible energy was dubbed dark energy. It seems that for the first half of cosmic history, gravity was winning. But as the universe grew and galaxies spread apart, gravity's influence weakened. About 6 billion years ago, the constant repulsive push of dark energy became dominant, and the universe began to accelerate. This paints a picture of our ultimate future. A big freeze, where the universe expands forever at an ever-increasing rate, until the sky, outside our own local group of galaxies, becomes empty and dark. And this mysterious dark energy is now at the heart of the Hubble tension. We have journeyed to the edge of the cosmos and the beginning of time. And now, we come to the most speculative part of our story, a question whispered at the fringes of cosmology. Does life influence the expansion of the universe? In mainstream science, the answer is no. But the Hubble tension opens a door to more philosophical lines of thinking, through something called the anthropic principle. The principle simply states that the conditions we observe in the universe must be compatible with our own existence. Scientists have long been puzzled by the apparent fine-tuning of the universe. The fundamental constants of nature seem to have values that fall within an extraordinarily narrow range that permits life. If dark energy were just a little stronger, galaxies never would have formed. If it were weaker, the universe might have collapsed on itself long ago. We live in a Goldilocks universe where the conditions are just right. This is where we can connect back to the Hubble tension. Perhaps the conflict between the early and late measurements is a signature of some new physics, like early dark energy, that was essential to striking the right balance for life to emerge. In this view, we are not causing the expansion to behave strangely. Instead, we are a asterisk consequence of that strange behavior. Our existence might depend on a universe with this exact cosmic tension. The fact that the expansion seems wrong might be the very reason we are here to notice it. This is, of course, deep speculation. It is philosophy as much as science. But it's a story that the current crisis in cosmology allows us to tell. We are left standing at a crossroads. In one direction, a universe whose childhood predicts an expansion of 67 kilometers per second per megaparsec. In the other, a universe whose adulthood is racing along at 73. Between them lies a chasm in our understanding. For years, scientists hoped better data would close this gap. But with every new observation from telescopes like JWST, the opposite has happened. The tension has grown stronger. This is not a failure of science. It is its strength. It's in these moments of crisis, when trusted theories break down, that the greatest leaps forward are made. The Hubble tension is a quiet but insistent clue, telling us that there is something fundamental about the cosmos we have missed. Some speculate the tension may yet fade with new ways of measuring, but for now, the most precise methods remain in conflict. The universe is expanding wrong, and scientists are concerned. But they are also thrilled. Because this cosmic mystery is a gift. It's an invitation to look deeper, to question our assumptions, and to perhaps discover a more complete story of our universe. This is a story that is unfolding in real time. We are on a journey to the edge of knowledge, and if this kind of calm exploration helps you unwind, I hope you'll consider following along. The answer is out there, written in the stretching of spacetime and the light of distant stars. And the hunt for it has just begun. The invisible force tearing our universe apart. There are forces in the universe that build things, that gather dust into stars and shape the architecture of galaxies. But there are other forces, quieter ones, that seem to work in the opposite direction. What if the most powerful influence in the cosmos is not one of creation, but of dissolution? An invisible, untouchable energy woven into the very fabric of reality, whose only purpose appears to be to push everything apart. A quiet force that is, at this moment, stretching our universe. In 1998, astronomers pointed their telescopes toward the distant light of dying stars. They were hoping to answer a simple question: is the universe running out of steam? For a long time, the assumption was yes. Gravity, the force that pulls everything together, should have been acting as a brake on the expansion that began with the Big Bang. But in 1998, those astronomers witnessed something that did not fit. The universe wasn't slowing down. It was speeding up. An invisible force is pushing galaxies apart, faster and faster, and scientists have almost no idea what it is. This is the story of that force, dark energy. The stable universe and the great expectation. For most of human history, the universe seemed to be a place of comforting stability. The stars moved in predictable patterns, and the cosmos felt eternal. Even when we learned in the early 20th century that the universe was expanding, a core assumption remained. Gravity was still in control. Think of it like this. You throw a ball into the air. It slows, stops, and comes back down. Gravity pulls on it. If you throw it hard enough to escape the Earth, you would still expect it to be slowing, even just a little, as gravity gently tugs on it from far away. For decades, this was the story of the cosmos. The Big Bang was the throw, and the galaxies were the ball. For 13.8 billion years, the universe had been expanding, but the combined gravity of every star and galaxy had to be acting as a brake. The only real question was how it would end. Would gravity eventually win, halting the expansion and pulling everything back into a Big Crunch, a reverse of the Big Bang? Or would the expansion just slow down forever, coasting into a cold and quiet future known as the Big Freeze? Those were the two possibilities. A final collapse or an eternal slowdown. Albert Einstein had wrestled with this problem. When he first developed his theory of general relativity, the math told him the universe must be either expanding or contracting. But this went against the idea of a static, unchanging cosmos. To make his equations match what was believed at the time, he added a little something extra. He called it the cosmological constant. It was a hypothetical energy, a kind of anti-gravity built into empty space, that would perfectly balance gravity and keep the universe still. Then, in 1929, the astronomer Edwin Hubble provided clear proof. He observed that distant galaxies were all moving away from us. The universe was expanding. There was no need for a balancing act. Faced with this evidence, Einstein removed the cosmological constant from his work, later calling its introduction his biggest blunder. And so, for the next 70 years, cosmology moved forward with a single, clear assumption. The universe was expanding, but gravity was fighting back. The expansion was slowing down. The only task left was to measure by how much. In the 1990s, two teams of astronomers set out to do just that. One was the Supernova Cosmology Project, and the other was the High-Z Supernova Search Team. Their goal was simple: to measure the cosmic slowdown. They had no idea they were about to find that everyone had only seen half of the picture. The impossible discovery. To measure the slowing of the universe, you need a special kind of yardstick. You need something in the deep cosmos that shines with a known, predictable brightness. An object that works like a standard candle. Imagine you are in a dark field, looking at a distant light. You can't tell if it's a dim bulb up close or a bright bulb far away. But if you knew every bulb in the field was exactly 60 watts, you could measure its faintness and know its distance with certainty. Astronomers found their 60-watt bulb in a specific kind of stellar explosion, a Type Ia supernova. These explosions happen when a small, dense star called a white dwarf pulls matter from a companion star. It grows heavier and heavier until it reaches a precise mass, about 1.4 times the mass of our Sun, and then ignites in a thermonuclear explosion. Because they all explode at that same mass, they all reach nearly the same peak brightness. They are the universe's standard candles. The plan for both teams was elegant. They would find dozens of these distant supernovae and measure their redshift, how much their light has been stretched by the expansion of space. This tells you how fast they are moving away. Then, they would measure their apparent brightness to determine their actual distance. By comparing these two values, they could map the expansion history of the universe. They expected to find that the most distant supernovae were brighter than their redshifts suggested. This would mean they were closer than expected, proving the expansion had been faster in the past and was now slowing down. As the data came in, both teams noticed something puzzling. The distant supernovae were not brighter than expected. They were dimmer. Consistently, quietly, inexplicably dimmer. The implication was profound, but simple. For a standard candle to appear dimmer, it must be farther away. For these supernovae to be even farther away than their redshifts predicted, it meant that the space between them and us had stretched more than expected. The expansion of the universe hadn't been slowing down. In the billions of years the light had been traveling to us, the expansion had been speeding up. It was a result so contrary to everything that was understood, the teams spent months looking for a mistake. They checked their math. They looked for intervening dust. They questioned their own work. There was no error. Both teams, working independently, came to the same conclusion. In 1998, they announced their findings. The expansion of the universe is accelerating. The discovery was so transformative that 3 of the leading scientists were awarded the 2011 Nobel Prize in Physics. But their work didn't answer a question. It created one of the biggest in all of science. Gravity pulls things together. What was this invisible force pushing everything apart? They gave it a name, a placeholder for something not yet understood. They called it dark energy. The scale of the mystery. The name, dark energy, is a quiet admission of how little we know. It doesn't describe what it is, only what it does. It's dark because we can't see it or detect it with any form of light. It's energy because it acts like a negative pressure, a repulsive force that opposes gravity. With this discovery, cosmologists began to recalculate the energy budget of the entire universe. What they found was humbling. All the things we have ever seen, every star, planet, and galaxy, make up just 5% of the cosmos. The rest is made of two mysteries. About 27% is a substance called dark matter, an invisible scaffolding whose gravity holds galaxies together. We don't know what it is, but we can see its effects. That leaves the largest share. A staggering 68% of the known universe is this new, baffling thing, dark energy. This tells a quiet story. For all of human history, we have been looking at the 5% of reality we can see, unaware of the 95% that truly governs the cosmos. So, what could this force be? The leading idea takes us back to Einstein and his biggest blunder. Perhaps the cosmological constant was correct after all. According to quantum physics, empty space isn't truly empty. It's a fizzing sea of virtual particles. This quantum foam could give space itself a fundamental, intrinsic energy. This is called vacuum energy. If this is dark energy, it has a strange property. As the universe expands, matter gets diluted. But if dark energy is a property of space itself, then as you get more space, you get more dark energy. The total amount increases as the universe grows. Think of it as a cosmic tug of war. In the early universe, matter was packed together tightly, and its gravity was dominant. For the first 9 billion years, the expansion was, in fact, slowing down. But as space expanded, matter spread out, and its gravitational pull weakened. About 5 billion years ago, a tipping point was reached. The repulsive push of dark energy became stronger than the pull of gravity. The brakes came off, the accelerator was pressed, and the universe began to speed up. Einstein's discarded idea is now the cornerstone of our standard model of cosmology. The case for acceleration. A claim as profound as an accelerating universe requires more than one line of evidence. If it were true, the signs should be written elsewhere in the cosmos. The first stop was the afterglow of the Big Bang, the cosmic microwave background, CMB. This is the oldest light in existence, a snapshot of the universe when it was just 380,000 years old. At first glance, it is almost perfectly uniform. But detailed maps revealed tiny temperature fluctuations, the seeds of all future galaxies. By studying the size and pattern of these fluctuations, cosmologists can determine the universe's fundamental properties. Their findings were a perfect fit for a universe made of about 5% normal matter, 27% dark matter, and 68% dark energy. The CMB confirmed the supernova results with quiet precision. There was another piece of evidence hiding in the way galaxies are arranged. In the early universe, sound waves rippled through the hot, dense plasma. These are called baryon acoustic oscillations, BAO. When the universe cooled and became transparent, these ripples were frozen in place, leaving behind a preferred distance between galaxies. This distance acts as a standard ruler for the cosmos. By measuring the apparent size of this ruler at different times in cosmic history, astronomers can map the expansion of the universe in a way that is completely independent of supernovae. Surveys that have now mapped millions of galaxies have used these baryon acoustic oscillations to reach the same conclusion. From exploding stars, to the afterglow of the Big Bang, to the clustering of galaxies, 3 different lines of evidence all converge on the same strange reality. Something is pushing our universe apart. The deepening cracks in the cosmos. Just as this new picture of the universe began to feel settled, new questions emerged. These were not minor details, but quiet puzzles that suggest the story is not over. The first is a question of timing. For the first 9 billion years, gravity was in control. Only in the last 5 billion years has dark energy taken over. But why now? Why do we happen to be living in the brief cosmic era where matter and dark energy have a comparable influence? Scientists are often suspicious of such coincidences. The fact that dark energy's rise happens to coincide with the era of life capable of observing it feels too convenient, hinting that our theory may be missing a piece. Then there is the Hubble tension. This is a persistent disagreement in the measurement of the universe's current expansion rate. When we measure it using nearby objects like supernovae, we get one number. When we infer it from the physics of the early universe, based on the cosmic microwave background, we get a slightly different number. For years, it was hoped the values would converge. Instead, as measurements have become more precise, the tension has remained. It is a quiet but stubborn problem that suggests either our measurements have a subtle flaw, or our model of the cosmos is incomplete. And beneath it all is the deepest mystery. While the cosmological constant is the leading candidate for dark energy, it has a major problem. When physicists try to calculate its theoretical value from quantum mechanics, the number they get is about 10 to the power of 120 times stronger than what we observe. This has been called the worst theoretical prediction in the history of physics, and it suggests we are missing something profound about how gravity and the quantum world connect. Perhaps dark energy is not a constant. Some have proposed a new energy field, nicknamed quintessence, that could change over time. Or perhaps there is no dark energy at all, and what we see is a sign that our theory of gravity needs to be revised. For years, these puzzles have lingered at the edges of cosmology. But recently, the plot has taken a new turn. The plot twist. For more than 20 years, cosmic acceleration has been a cornerstone of cosmology. But in science, no fact is ever truly settled. In late 2025, a team of astronomers led by Professor Young-Wook Lee at Yonsei University published a study that challenged this foundation. Their paper suggests that the universe's expansion may not be accelerating after all. Their argument returns to the original evidence, the type Ia supernovae. The discovery in 1998 assumed they were perfect standard candles. But Lee's team proposed that there is a subtle, age bias. A supernova that explodes in a young galaxy might have a slightly different brightness than one in an old galaxy. The original studies didn't fully account for the age of the host galaxies. Lee's team reanalyzed the data, applying a correction based on the age of the stars that produced the explosions. What they found was remarkable. Once this age bias was accounted for, the evidence for acceleration seemed to vanish. Their analysis suggested that the universe may have already passed its phase of acceleration and transitioned into a state of decelerated expansion today. If this is confirmed, it would be a major shift in our understanding. However, and this is a critical point, these findings are new, controversial, and have not yet been accepted by the wider scientific community. They rely on a complex correction that other experts are now carefully examining. At the same time, other experiments are providing their own clues. The Dark Energy Spectroscopic Instrument, or DESI, has created the largest 3D map of the universe, charting nearly 15 million galaxies to trace dark energy's influence over 11 billion years. The latest results from DESI, released in early 2025, are fascinating. When DESI's data is looked at by itself, it is consistent with the standard model of constant dark energy. But when combined with other observations like the CMB and supernovae, a different picture emerges. The combined data shows hints that dark energy is not a constant, but is evolving and perhaps weakening over time. The statistical significance for this evolving dark energy is growing, but it has not yet reached the 5 sigma gold standard needed for a discovery. The hints are persistent, but not yet definitive. We have moved from a simple story of a runaway universe to a much more nuanced picture. Is dark energy a constant? Is it a fading force? The only thing certain is that the universe is far stranger than we imagined. The ultimate fate of the universe. The true nature of dark energy holds the key to the ultimate fate of everything. Depending on what it is, the end could come in fire, ice, or a quiet tearing apart. First, let's assume the standard model is correct and dark energy is a fixed, unchanging property of space. In this scenario, the future is known as the Big Freeze, or heat death. The accelerating expansion will continue forever. Distant galaxies will recede from us, eventually vanishing from our sky. Over trillions of years, the stars within our own galaxy will burn out. The universe will become a dark, cold place, populated by the quiet husks of stars. Eventually, even these may decay, and the universe will become a thin, featureless soup of particles, growing ever colder and emptier as it expands into infinity. But what if dark energy is not constant? A more speculative and unsettling possibility is called phantom dark energy, where its density increases over time. This would lead to a fate known as the Big Rip. The acceleration itself would accelerate until the repulsive force of dark energy could overcome everything. It would first pull galaxies apart, then solar systems. In the final moments, planets, stars, and even the atoms that make up our bodies would be gently torn asunder. The fabric of spacetime itself would dissolve. The latest evidence, however, with its hints of a weakening dark energy, opens the door to a third possibility. If dark energy is a fading force, the cosmic tug-of-war could tip back in gravity's favor. The expansion could slow, stop, and reverse. This would lead to the Big Crunch. The universe would contract, with galaxies rushing toward each other. The sky would grow brighter than the surface of a star as all of existence was squeezed back into an infinitely hot, dense point, mirroring the moment of creation. Some theories even speculate this could lead to a Big Bounce, a new universe born from the ashes of our own in an eternal cycle of endings and beginnings. Freeze, rip, or crunch. 3 possible futures, each a quiet meditation on the scale of time. The final chapter of the universe has not yet been written. Its story will be traced by the invisible influence of dark energy. The quest to understand dark energy is at the very front line of modern cosmology. We are building new observatories, like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope, to map the universe with greater precision than ever before. What we find will not only tell us about the fate of our universe, but will almost certainly begin a new chapter in our understanding of physics. If this kind of calm exploration of the cosmos helps you unwind, consider subscribing for more journeys into the quiet corners of science. And wherever you are right now, feel free to share your thoughts on these unfolding mysteries in the comments below. The story of dark energy is a quiet lesson in humility. It is a reminder that what we can see is not all there is. We live in a cosmos where 95% of reality is made of dark matter and dark energy, substances whose nature remains a deep enigma. For centuries, we saw the universe as a grand machine, unfolding in a predictable way. The discovery of dark energy showed us a cosmos that is not just strange, but quietly defiant of our expectations. It has forced us to reconsider our most fundamental ideas of space, time, and gravity. But this is not a failure of science. It is science working as it should. It is a continuous process of discovery, a journey from one level of understanding to the next. The existence of dark energy is a sign that we are pushing at the true boundaries of knowledge, asking questions so deep the answers are guaranteed to change how we see everything. We are quiet observers, piecing together a story told in the light of dying stars across billions of years. The investigation has just begun. Life's secret mission is to unravel the universe. Life appears to be a builder, a creator, a quiet force for order in a universe that seems to prefer chaos. From the workings within a single cell to the complexity of a forest or a city, the story of life looks like one of constant construction. We build, we grow, we organize, we hold back the slow tide of decay. But there is another way to look at this. What if this constant effort isn't a rebellion against the universe's final direction? What if life is the most sophisticated tool the universe has produced to achieve that direction? This is a quiet and humbling idea. That life has an unconscious mission. A mission not to create, but to unravel. A mission to help the universe fulfill its nature. The grand deception. From our perspective, life feels like the hero of the cosmic story. The one thing that stands against the vast, cold emptiness of space. Where the cosmos is content with simplicity, barren rock, thin gas, empty void, life is an artist of complexity. It takes simple molecules and forges them into the quiet architecture of a tree. It arranges mundane atoms into a brain capable of thinking about the stars where those atoms were born. Think of it like building a sandcastle on a beach. The universe is the incoming tide, patiently working to flatten everything into a smooth, uniform state. And life? Life is the builder, slowly creating pockets of intricate order, holding back the waves for a quiet, fleeting moment. This is the story told by evolution. A story of growing complexity over billions of years. From simple, single-celled organisms, life branched into a quiet variety of forms. It developed photosynthesis, multicellularity, nervous systems, and eventually, consciousness and technology. Each step looks like a victory against disorder, a move away from the simple chemistry of early Earth and towards greater structure. We see ourselves as the pinnacle of this process. We build cities. We create information networks. We launch probes into the emptiness we seem to be fighting. Our existence feels like an act of rebellion. A statement that order is not only possible, but meaningful. But this heroic story might only be one half of a much larger truth. It focuses on the intricate sandcastle, but it ignores what the builder is doing to the rest of the beach. To understand the full picture, we have to look at life not from our perspective, but from the perspective of the universe itself. And to do that, we first need to understand one of the most fundamental laws in the entire cosmos. The unbreakable law. In the 19th century, physicists described a law of nature so fundamental it governs everything, from the cooling of coffee to the life of stars. It's called the second law of thermodynamics. It describes the direction in which everything seems to go. It is the universe's arrow of time. At its heart is a concept called entropy. Entropy is a physical measurement, but it's often described with a single word: disorder. The second law states that in any isolated system, a system that doesn't exchange energy with its surroundings, the total amount of entropy will always increase over time. Order gives way to chaos. It is not a suggestion, it is a statistical certainty. There are simply more ways for things to be disordered than to be ordered. To understand this, think of a room. Imagine it is perfectly clean and organized. This is a low entropy state. There are very few ways for a room to be perfectly clean. Now, live in that room for a week. Clothes end up on the floor. Papers accumulate. The room becomes messy. It has transitioned to a high entropy state. Why? Because there are vastly more ways for a room to be messy than to be clean. The universe, as a matter of probability, trends toward the mess. Or think of a drop of cream in a cup of black coffee. At first, you have an ordered system. The cream is separate from the coffee. But wait a moment. The cream swirls and dissipates until the entire cup is a uniform color. The system has reached maximum entropy. A perfect disorder. Now, try to reverse it. Could you stir the coffee so that all the cream molecules gather back into a single drop? The odds are so low that it will never happen. The arrow of time points in one direction, towards the mixed coffee. This isn't just about messes. It's about energy. Think of a bouncing ball. With each bounce, some energy is lost, dissipated into the floor and the air as a tiny puff of heat. Heat is the most disordered, highest entropy form of energy. The useful, ordered energy of the bounce has been degraded into useless, disordered thermal energy. Now, let's apply this law to the universe. Our best understanding is that the universe began 13.8 billion years ago in a state of very low entropy, a hot, dense, and remarkably uniform point. Since that moment, the universe has been expanding, cooling, and becoming more disordered. Stars are burning their ordered fuel and radiating it away as disordered heat and light. For a long time, the logical conclusion was thought to be a state known as the heat death of the universe, where everything would fade into a cold, uniform emptiness. But this may not be the final story. Recent discoveries are beginning to suggest a different path. Data from observatories and new theoretical work from physicists like Henry Tai at Cornell and researchers at Yonsei University have questioned the idea of endless acceleration. Evidence gathered in 2025 and 2026 suggests the universe's expansion may be slowing down. The mysterious force we call dark energy may not be a constant, but something that weakens over time. Some models now indicate the universe could be on a trajectory to stop expanding and begin collapsing back in on itself, ending in a big crunch billions of years from now. The ultimate fate of the cosmos is not settled. It remains one of the deepest questions science is still working to answer. So, if the universe is on this grand, uncertain journey of transformation, how is life possible at all? The plot twist. The apparent conflict between life's complexity and the universe's drive for disorder was explored by the physicist Erwin Schrödinger in his 1944 book, What is Life? How can life exist in a universe governed by the second law of thermodynamics? The answer is found in a quiet detail of that law. The second law applies to closed systems. But living things are not closed systems. You are an open system. You constantly exchange matter and energy with your environment. You eat, you drink, you breathe. Life doesn't violate the second law, it uses a loophole. Schrödinger said that life feeds on negative entropy. This was a poetic way of saying that organisms maintain their own internal order by taking order from their surroundings and exporting a greater amount of disorder back out. Think of it like a plant. A plant can build a beautiful, ordered structure, a pocket of low entropy. But to do so, it makes the universe as a whole more disordered. The ultimate source of the order it feeds on is the sun. The sun sends out a constant stream of highly concentrated, low-entropy energy as sunlight. A photon arriving from the sun is a very high-quality, ordered packet of energy. A plant, through photosynthesis, captures that photon. It uses that energy to do something remarkable. It takes disordered carbon dioxide and water and forges them into a complex, highly structured sugar molecule. It creates order. But the energy doesn't vanish. The plant uses the sugar to live, and that energy is eventually released back into the environment. But it's no longer a high-quality solar photon. It's now released as low-quality, diffuse, high-entropy infrared radiation, waste heat. The plant takes in one high-quality photon and spits out many low-quality photons into the cold of deep space. The transaction is complete. The plant has created a tiny pocket of local order. But in the process, it has degraded a highly ordered packet of energy and increased the overall entropy of the universe by a much larger amount. Life doesn't fight the second law. It is an engine for fulfilling it. It is one of the most efficient entropy-producing machines we know of. This idea has been taken a step further by physicists like MIT's Jeremy England. His work suggests that the emergence of life might be an inevitable consequence of thermodynamics. His models suggest that when a group of atoms is exposed to an external energy source, like the sun, it will naturally tend to restructure itself to get better at absorbing and dissipating that energy. In other words, the universe might favor the formation of systems that are good at increasing entropy. And what is one of the best systems for dissipating energy? Life. A rock in the sun will absorb sunlight and radiate heat away, but it's a slow, inefficient process. A plant, on the other hand, is a marvel of dissipative engineering. It uses energy to power chemical reactions, to pump water, to grow, and to reproduce. It is a far more effective channel for degrading the sun's energy. From this perspective, as England puts it, the origin of life should be as unsurprising as rocks rolling downhill. Physicist Karo Michaelian has proposed that life's fundamental building blocks, DNA and RNA, may have been successful at first because they were excellent at absorbing ultraviolet radiation on the early Earth and converting it into heat. Replication, in this view, came later because, as England notes, a great way of dissipating more is to make more copies of yourself. Life isn't a miraculous anomaly. It is the plot twist in the cosmic story. It appears to be building order, but its secret function, its deeper purpose, is to accelerate the creation of chaos. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. We journey to the edge of science, exploring the biggest questions in the cosmos. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The planetary engine. Once we accept this shift in perspective, that life is an engine of entropy, we can begin to see its work everywhere, from a single molecule to the entire planet. The secret mission is a planet-spanning process. First, let's look at the entire living world. The Earth's biosphere, as a whole, is a single, enormous system whose primary function is to capture the low-entropy energy of the sun and degrade it into high-entropy heat. Think of the food chain. Sunlight is captured by plants. That stored energy is eaten by herbivore. The herbivore uses the energy to live and generate body heat, dissipating it further. A carnivore might eat the herbivore, continuing the process. At each step, a huge portion of the energy is lost as waste heat. The entire ecological web is a cascade of ever-increasing entropy. The great cycles of the planet, the carbon cycle, the water cycle, are all intertwined with life. Forests influence weather patterns. The transpiration from countless leaves is a massive engine for dissipating thermal energy. For billions of years, the collective action of life has been re-engineering the planet's surface to make it an ever more efficient channel for processing solar energy. And then, humanity entered the scene. If life is an entropy accelerator, then human civilization represents a change in scale. Early life learned to use the real-time energy of the sun. We have learned to do something more potent. We have learned to tap into the planet's savings account. Fossil fuels, coal, oil, and gas, are ancient, buried sunlight. They are the concentrated, low-entropy energy captured by plants millions of years ago and locked away. When we burn them, we are releasing this ancient, ordered energy in a geological instant. Our industrial civilization is a furnace of unprecedented scale. Our cities radiate immense quantities of heat. Our computers and data centers consume colossal amounts of energy, with every calculation ultimately ending in the production of disordered waste heat. We are, without doubt, the greatest entropy producers the planet has ever known. This brings us to a quiet, speculative question. What role does life play on a cosmic scale? In the past, when an eternal, accelerating expansion seemed likely, some wondered if life's entropic output could somehow aid that process. But with our understanding of the cosmos now shifting, that idea no longer holds. The forces driving the universe's fate, gravity and the evolving nature of dark energy, are immense, operating on a scale far beyond life's influence. Life's role is not to steer the cosmos. Its impact is local, but that does not make it insignificant. The universe needed a way to go from the highly ordered state of the Big Bang to a more disordered one. It had stars, which do the job slowly. But in life, the universe may have found a catalyst, a way to speed up the process on a planetary scale. In this view, the universe isn't just a stage for life. The universe might be using life to more efficiently unfold its own nature. The new perspective. So, where does this leave us? If our deepest impulse, to live, to grow, to build, is ultimately serving the universe's agenda of unraveling, is our existence rendered meaningless? Perhaps the opposite is true. This perspective doesn't devalue life, it reframes its significance. It challenges the idea that we are separate from the universe, an accident fighting a pointless battle. Instead, it places us as a fundamental, intimate expression of the universe and its most basic laws. Our drive to survive is not ours alone, it is the universe, acting through us. The energy that compels us to build cities, to write symphonies, to understand our origins. That is the cosmos, exploring the most complex ways to unfold its own destiny. We are not fighting the current, we are the current. Our local order is the very thing that makes the river of time flow faster. There is a quiet beauty in this. Life is a brilliant, dazzling flame. And the nature of a flame is to burn through fuel, to create light and heat, and in doing so, to exhaust itself. The brighter the flame, the faster it consumes its fuel. We are that brightness. Our struggle for existence, our moments of joy and sorrow, our quest for knowledge, they are all part of the shimmering light of that flame. They are no less beautiful for being part of a larger, impersonal process. In fact, they may be more meaningful, because they connect our tiny lives to the grand, sweeping arc of cosmic history. So the next time you look up at the night sky, at the distant stars, don't feel like an isolated observer peering into an empty void. Feel the connection. You are made of the ashes of ancient stars, living on a planet powered by a nearby star. Every breath you take, every thought you have, is a quiet transaction with the cosmos. You are taking a spark of stellar fire, a packet of low-entropy light that has traveled millions of miles, and you are transforming it into the impossibly complex and ordered miracle of your own consciousness. And in that same breath, you exhale a little puff of warmth, a little cloud of disordered chaos, back into the void. You are fulfilling a function woven into the fabric of your being. And understanding that, truly understanding it, is a profound, a humbling, and a strangely comforting thought. Fall asleep to the universe's definition of you. There is a quiet question that can arise when looking up at a sky filled with stars. A question about scale and place. In the grand design of everything, what are we? The universe does not answer in words. It answers in the language of physics, of starlight, and of time itself. It tells a story that connects a single breath to the birth of stars, a story written in unbreakable laws that govern everything from a cooling cup of coffee to the slow fade of a galaxy. Tonight, there is nothing to solve. There is only rest. We will take a quiet journey past the edge of the sky, into the silent expanse of the cosmos. We are going there to find that definition. So find a comfortable position. Let your eyes close. There is no need to hold on to any thought. Allow my voice to be a gentle guide, as we drift through the cosmos, and listen to what it has to say. If you have ever held a hot cup of tea, you have felt its warmth seep into your hands. You have also noticed that, little by little, that warmth fades. The drink cools, its heat spreading out into the room until it is the same temperature as everything around it. In that simple, quiet moment, you have observed one of the most profound laws of the universe. It is the law that governs everything, from that cooling cup to the life of the most distant star. And as we will discover, it is a law that ultimately defines us. This gentle, inevitable spreading of energy, this journey from order to disorder, is the current upon which all of existence flows. And tonight, we will learn how you, in your very being, are a remarkable and complex structure built by that cosmic current. The cosmic river, understanding entropy. Let us begin with an image of the universe at its origin. Billions of years ago, at the very beginning, something incredible happened. A single point, unimaginably hot and dense, began to expand in an event we call the Big Bang. This was not an explosion in space, but an expansion of space itself. It was as if a single, hot droplet was placed in the center of a vast, still, cosmic lake. In that initial moment, the universe was a place of immense order. All the energy that would ever exist was concentrated in a state of near-perfect uniformity. But just like the hot cup of tea, the universe could not remain this way. The fundamental rules of existence, the laws of thermodynamics, began to act. The most important of these for our story is the second law of thermodynamics. It is a simple and inescapable truth. In a closed system, things tend to move from a state of order to a state of disorder. The scientific measure for this disorder is called entropy. You understand this intuitively. It is why a carefully built sandcastle is eventually claimed by the wind and the waves, its grains scattering back across the beach. It is why a drop of ink in a glass of water does not stay as a neat sphere, but instead spreads out until the entire glass is a single, uniform color. Energy, like that ink, prefers to spread out. It seeks equilibrium. It moves from areas of high concentration to areas of low concentration. It is the universe's natural tendency to smooth things over. Think of it as the universe taking a slow, deep exhale. The initial, hot, dense state of the Big Bang was the breath in. For the last 13.8 billion years, the universe has been exhaling. The heat is dissipating. The energy is spreading out. This flow, this journey from concentrated order to diffuse disorder, gives us the arrow of time. It is the reason the past is different from the future. It is the direction of the cosmic river. On our journey, we can see the brilliant lights we call stars. Each one is a magnificent testament to this law. A star is a huge, concentrated ball of energy. For millions or billions of years, it radiates light and heat out into the cold emptiness of space. It is a bonfire in the cosmic night, sharing its warmth, spreading its order into the void. Eventually, it will run out of fuel. It will cool, and its energy will have been distributed across the cosmos. This process is happening everywhere. The ultimate, theoretical end of this journey, many trillions of years from now, is a state physicists call the heat death of the universe. It is a state of perfect equilibrium. A universe where all the energy has spread out so completely that everything is the same, uniform temperature, just a fraction of a degree above absolute zero. The cosmic river will have finally reached the sea. This might sound bleak, but it is not the whole story. Because in this vast, cooling river of entropy, something remarkable happens. In certain quiet corners, little pockets of complexity begin to form. Eddies of breathtaking order appear, sustained by the very flow that seeks to dissolve everything. These pockets, these islands of intricate structure, are called life. And you are one of them. The island of order, life is organized matter. As we continue to drift, let us adjust our focus toward a small, blue and white marble, orbiting an ordinary star. Our Earth. From here, we can see the next part of the universe's definition. From a cosmic perspective, before anything else, life is organized matter. After the Big Bang, the universe contained mostly the simplest atoms, hydrogen and helium. For millions of years, they floated in vast clouds. But gravity, that gentle, persistent force, began to pull them together into the first stars. Inside the fiery hearts of those stars, through the intense pressure of nuclear fusion, new, heavier atoms were forged. Carbon, oxygen, nitrogen, iron, the very elements that are, right now, inside of you. When those first giant stars reached the end of their lives, they exploded in brilliant supernovae, scattering these newly forged elements across the cosmos like a celestial gardener sowing seeds. This cosmic dust mingled with new clouds of hydrogen and eventually formed new stars and new planets. Your body is made of this stardust. The carbon in your skin, the calcium in your bones, the iron in your blood, all of it was created in the heart of a star that lived and died billions of years ago. But you are not a random collection of stardust. You are organized stardust. On our planet, bathed in the steady energy of our sun, and mixed in liquid water, these elements began to connect. They formed vast, complex chains of atoms, arranged in specific, intricate patterns. These are the molecules of life: proteins, lipids, and the spiraling staircase of DNA. Imagine a box full of millions of individual letter blocks. If you shake the box, you will have a jumbled mess. That is a state of high entropy. But if you were to reach in and carefully arrange those blocks to spell out a story, that is organization. That is a state of low entropy. You are that story. From the smallest scale, you are a marvel of structure. Atoms are arranged into molecules. Molecules into the complex machinery of cells. Cells are arranged into tissues. Tissues are arranged into organs. And those organs work together to form you. A physicist might call this a hierarchical system of supramolecular structures. We can simply call it a remarkable achievement of order. This organization is not accidental. It is a response to its environment, much like a snowflake forms its intricate, six-sided pattern in response to the temperature and humidity of the air. It is matter finding a way to become complex, to build structures that are stable. So, as you lie here, feel the reality of this structure. The solidness of the bones that support you, the coolness of the skin that contains you, the rhythmic beat of the heart in your chest. Each is a testament to an unimaginable history of cosmic organization. You are not separate from the universe. You are the universe, having found a way to arrange itself into a thinking, feeling being. This is the first part of the cosmic definition. You are a pocket of profound and beautiful order in a universe that tends toward disorder. The water wheel, life as an energy processing system. An island of order, no matter how intricate, must contend with the sea. This magnificent structure that is you exists within the great cosmic river of entropy, which works tirelessly to break down complexity. This brings us to the next layer of the cosmic definition. Life is not a static structure like a crystal. It is a dynamic process. It is an energy processing system. Let us return to our analogy of the cosmic river, the flow of energy from order to disorder. Now, imagine placing a water wheel in that river. The river will flow downhill anyway. But the water wheel intercepts that flow. It catches the moving water and uses its energy to do something useful. It turns. It can grind grain or generate power. The water wheel does not stop the river. It borrows some of the river's energy as it flows by and uses it to perform work. You are that water wheel. Your existence is a process that intercepts the flow of energy in the universe and uses it to maintain your own ordered structure. The great physicist Erwin Schrödinger, in his 1944 book, What is Life?, described this perfectly. He said that a living organism feeds on negative entropy. The idea is wonderfully simple. To maintain your own internal order, you must import order from your surroundings. You must consume high-quality, organized energy. For life on Earth, the primary source of this ordered energy is the sun. Plants, through photosynthesis, capture this high-quality energy. They use it to take simple, disordered molecules, carbon dioxide and water, and build them into complex, ordered molecules of sugar. They are storing the sun's order in a chemical form. When you eat a plant or an animal that ate a plant, you are taking in that stored order. Your body then carefully breaks those molecules down, releasing the stored energy in a controlled way. You use that energy for everything. You use it to power the billions of chemical reactions in your cells, to repair tissues, to pump your blood, to think. You use it to push back against the constant, gentle pressure of entropy. And after you have used the energy, you release it back into the environment. But you release it as low-quality, disordered energy. You release it as gentle, diffuse heat. Every moment, your body, which is warmer than its surroundings, is radiating a faint cloud of warmth. You are taking in order, and you are exporting disorder. In a fascinating way, you actually help the river on its journey. By taking a concentrated form of energy and breaking it down into diffuse heat, you accelerate the universe's journey toward higher entropy. The physicist Jeremy England has a beautiful theory about this. He suggests that life isn't a fluke. It's a natural consequence of physics. He argues that when a group of atoms is driven by an external source of energy, like the sun, it will naturally tend to rearrange itself into structures that are better and better at absorbing and dissipating that energy. From this perspective, life is the universe's most creative way of dissipating energy. You are not fighting the universe. You are the universe, having evolved a breathtakingly complex system for processing energy. Your existence is a fundamental expression of its laws, as natural as a river flowing to the sea. Feel that now. The gentle warmth of your own body. That is the signature of your life, the exhaust of the intricate engine that is you. The cosmic gardener. Life as a local entropy reducer. We can now weave these two threads together. We have seen that you are an island of organized matter, and a dynamic system that maintains this order by processing energy. This leads to the heart of the universe's definition of you. You are a local entropy reducer, asterisk. This sounds like a contradiction. We've established that the universe's total disorder is always increasing. That is the unbreakable second law. But the law allows for a loophole. While the total entropy of a closed system must increase, small, local pockets within it can become more ordered, as long as they export an even greater amount of disorder to their surroundings. You are that local pocket. Inside your body, right now, billions of your cells are working to repair damage, to clear out waste, to maintain the intricate structures that allow you to live. You take the disordered mix of molecules from food and you organize them into new skin cells, new blood cells, new memories. You are creating order from chaos. You are reducing entropy locally. You are not defying the second law. You are a perfect example of it. You are a living demonstration of how the universe can create breathtaking complexity in one place, by increasing simple disorder in another. For every bit of order you create inside yourself, you must pay the universe by creating more disorder outside yourself. This is the heat you radiate. Let's zoom out from the individual and see this principle at work on a planetary scale. For billions of years, life on Earth has been acting as a great, collective entropy reducer. Early life took the sun's harsh energy and used it to build ordered biomass. In the process, it released gentle heat, cooling the planet. Life terraformed our world, making it the temperate, hospitable place we know. It is a planetary-scale gardener, tending its own oasis of order. This changes our perspective. We are not struggling against a hostile universe. We are an expression of it. The tendency for entropy to increase is not a destructive force. It is the creative engine that drives the formation of complexity. The flow of the river is what allows the water wheel to turn. You are not an anomaly. You are the universe's way of creating localized pockets of wonder. You are a pattern the cosmos has formed to more effectively move energy from a state of concentration to a state of diffusion. You are the universe's solution to a physics problem. And the solution happens to be beautiful. It happens to be conscious. It happens to be you. The gentle ripple, the grand speculation. As we drift now, deeper into a state of rest, our exploration enters a more speculative realm. We have seen how life can change the chemistry of a planet. This begs a final question. If life can change a world, could it, in some small, collective way, influence the cosmos itself? This is where we move from established science into a beautiful thought experiment. The standard model of our universe says its expansion is driven by a mysterious force called dark energy. In this picture, life is an insignificant footnote, a brief chemical reaction on a speck of dust. But let's play with the ideas we've explored. We've established that life is the most efficient process we know of for increasing the universe's overall entropy. What if this is not just an accidental feature of life, but its fundamental cosmic purpose? Some thinkers have proposed that life is a viral phenomenon that might spread from star to star, and eventually, across a galaxy. A galaxy teeming with life would be a powerhouse of entropy production, absorbing starlight and processing matter on a scale we can barely conceive. Could this collective action of life create a gentle ripple in the fabric of spacetime? Could it subtly influence the expansion of the universe itself? Let me be clear that this is pure speculation. There is no evidence for this. It is a what if to hold as you drift off. It's an idea that reframes our existence, not as cosmic accidents, but as cosmic participants. It suggests that the impulse to live, to grow, and to create order might be a reflection of a deep, universal principle. It's a thought that suggests we are not just passengers, but perhaps part of the engine. And so, we drift back now, from the edge of galaxies to the quiet of your room. We have journeyed far, and found a definition written in the laws of the cosmos. What are you, in the grand scheme of it all? You are forged in the heart of a star. You are an island of breathtaking order in the universe's great river of time. You are an intricate machine powered by starlight, a process that turns energy into consciousness. You are a local entropy reducer, a fortress of order that pays a gentle tax of warmth to the cosmos. You are the universe's way of organizing itself into a small, warm, and wonderfully complex pocket, so that it might, for a brief moment, look back and wonder at its own magnificence. You are not a stranger here. Your existence is a fundamental and beautiful expression of the laws that govern everything. As you feel your body grow heavy, feel that gentle warmth you are releasing. That is your connection to the cosmos. It is the signature of your life, the soft exhaust of your inner flame. That is you, playing your part in the great, silent story of everything. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video. It helps others who are seeking rest to find their way here. And if you would like to continue these quiet journeys, perhaps consider subscribing. I often wonder where in the world you are listening from, so feel free to share in the comments below. It is a lovely thought, to know we are all under the same vast sky, pondering the same quiet mysteries together. But for now, just let it all go. Let the definitions dissolve. Let the thoughts drift away like distant stars. There is nothing left to do but rest. Let the universe hold you. Your body is pushing the universe apart. Listen. Go on, just for a second. That sound, that's your own life. It's a steady, rhythmic, biological machine, turning chemicals into motion, into pressure, into the flow of blood that keeps you alive. It's the most intimate metronome you'll ever know. But it's also something else. It's the sound of you pushing the universe apart. Every single beat sends a tiny, nearly imperceptible pulse of energy out into the cosmos. A whisper in the cosmic dark. But you're not alone. Right now, billions of human hearts are beating. Trillions upon trillions of other living things, from the frantic buzz of a hummingbird to the slow, deep thrum of a blue whale, are all doing the same thing. And they have been, for billions of years. An unbroken chorus of life, with each beat adding its own microscopic ripple to the fabric of spacetime. What if all this life, this constant, faint hum of existence across eons, isn't just a passive passenger in the cosmos? What if it's an active force, a co-conspirator in the grandest story of all? This is the story of whether your existence, combined with all life, is secretly accelerating the end of everything. It sounds like something straight out of science fiction, but it touches on one of the most profound and startling discoveries in history. For most of the 20th century, we thought we had the story figured out. The universe was expanding, sure, but it was a fight. A cosmic tug-of-war between the Big Bang's explosive momentum pushing everything out, and the relentless grip of gravity pulling it all back in. Every star, every galaxy, Every planet was a soldier on the side of gravity, trying to slow the expansion. The big question was, who would win? Would gravity eventually stop the expansion and yank everything back into a final, cataclysmic, big crunch? Or would the expansion win out, leaving the universe to grow colder and emptier forever? That was the battlefield. But in 1998, everything changed. We discovered the fight was rigged. The runaway universe. The discovery was one of the most jarring in all of physics. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using distant exploding stars, type Ia supernovae, to measure how the universe's expansion has changed over time. These supernovas are fantastic cosmic tools. They're standard candles, which means they all have roughly the same intrinsic brightness. By seeing how dim they look from Earth, we can figure out how far away they are. And by measuring their light's redshift, we can clock how fast they're moving away from us. The expectation was simple. The supernovae farthest away should look like they were receding faster than they should have been, because we'd be seeing them in the past, before gravity had more time to apply the brakes. But that's not what the teams found. The distant supernovae were dimmer, and therefore farther away, than they should have been. There was only one way to explain it. The expansion of the universe wasn't slowing down. It was speeding up. Imagine you toss a ball in the air. You expect it to slow down, hang for a second, and fall back. Now imagine that instead of slowing, it just takes off, faster and faster, as if it had a hidden rocket. That's what we learned our universe is doing. It's a runaway. This revelation was so massive it earned a Nobel Prize. It meant some other player was on the field, a mysterious, repulsive force that wasn't just fighting gravity, but completely overpowering it. Astronomers gave this mysterious something a name: dark energy. It's a simple name for a baffling mystery. What is it? The leading theory is that it's a property of space itself, an intrinsic energy of the vacuum. As the universe expands, more space gets created, and with it, more dark energy, which then pushes space to expand even faster. It's like a kind of anti-gravity. And according to our best measurements, this strange substance makes up just under 70% of everything in the universe. All the familiar stuff, atoms, stars, galaxies, you and me, that's less than 5%. We are just foam on a vast, dark, energetic ocean. This discovery rewrote the final chapter of the cosmos. Instead of a fiery big crunch, the dominant theory became the big freeze, or heat death. In this future, the accelerating expansion pulls everything apart. Galaxies will fly away from each other so fast that the light from one will never reach another. Eventually, anyone living in a galaxy would see only an endless, empty blackness beyond their own cosmic shores. Stars would burn out, the universe would grow colder and darker, and eventually, all useful energy would be spent. A slow, desolate, quiet end. But just recently, the story has gotten even weirder. New data from incredible observatories like the Dark Energy Spectroscopic Instrument, or DESI, have given us the first tantalizing hints that dark energy might not be constant. Some results suggest it might actually be weakening over time. If this holds up, it throws the future wide open again. It could mean the expansion might one day slow, stop, and reverse, sending everything hurtling back towards a big crunch after all. The final chapter isn't written yet. The big freeze is still the front runner. A dramatic big crunch is now back on the table as a possibility, and there are even more exotic, though less likely, ideas like a big rip, where the acceleration becomes so strong it tears atoms apart. But in all these stories, the driver is this huge, impersonal cosmic energy. Or is it? The energy of life. Let's come back to your heartbeat. This is where our story takes a turn from the facts of cosmology into a grand thought experiment. We're going to step away from the known and ask, what if? Every time your heart beats, it does about 1 joule of work. That's a tiny amount of energy, barely enough to lift an apple a few feet off the ground. It seems absurd to even say it in the same breath as the forces that move galaxies. But you aren't just one heartbeat. Your heart beats around 100,000 times a day. Over an 80-year life, that's almost 3 billion beats. 3 billion joules of work from your heart alone. And that's just a fraction of your body's total energy output. Every breath, every word, every thought flickering through your brain is a transfer of energy. Now, zoom out. You're one of over 8 billion people, all living, breathing, and metabolizing. But that's just us. Think of all the animals, the insects, the bacteria in the soil and oceans. The total biomass of life on Earth is estimated to be around 550 billion tons of carbon. All of it is a planetary-scale engine, constantly processing energy. Every living thing, from a cell dividing to a forest growing, adds a tiny bit of energy, as heat, motion, or radiation, into the system. This is the hum of the biosphere. A constant, low-level energetic buzz that's been going on for nearly 4 billion years. Think of the sheer number of heartbeats, wing flaps, and fin swishes over that immense time. It's an incalculable amount of biological energy, radiated out into space. It's an awesome amount of activity. But can it really matter to the cosmos? This is where we have to face the crushing, beautiful scale of the universe. The total mass of ordinary matter in the observable universe is around 1.5 times 10 to the 53 kilograms. That's a 15 with 52 zeros. The total biomass of Earth is about 10 to the power of 15 kilograms. Life on Earth, compared to all the regular matter in the universe, is a fraction so small it's basically 1 part in 10 to the power of 38. That's like comparing the mass of a single grain of sand to the entire Earth. Its gravitational influence is, for all intents and purposes, zero. So, case closed, right? Life is cosmically insignificant. But hold on, we're talking about dark energy. And dark energy isn't like gravity. It doesn't come from mass. It seems to be an energy of space itself, and it works by creating negative pressure. It pushes things apart. So the question isn't, how much does life weigh? But, what kind of energy does life produce? Could the collective energy of living things, this constant hum across eons, act in a way that's fundamentally different from a dead rock or a cloud of gas? Could it, somehow, contribute to that negative pressure? Let's be crystal clear. There is no known physics that would allow this. Mainstream science says biological processes are just complex chemistry, governed by the same fundamental forces as everything else. There's no special, life force, that can tweak the cosmos. In fact, you could argue life does the opposite. Life organizes matter, clumping it together into dense structures like trees and cities. This actually helps gravity fight expansion, though on a scale so comically microscopic it's completely irrelevant. So, from a purely scientific, evidence-based view, the answer is no. Your body is not pushing the universe apart. The energy is too small, the scale is too vast. But, is that really the end of the story? The arrow of causality. Maybe we've been looking at this completely backward. We've been asking if life can affect the expansion of the universe. But what if the expansion of the universe is precisely what allows for life? This is a concept called the anthropic principle. The weak version simply says that the conditions we observe in the universe have to be compatible with us being here to observe them. That sounds a bit circular, like saying, we're here because we're here, but it has staggering implications. Think about the value of dark energy. If it were much stronger, the universe would have expanded so fast that galaxies and stars never would have formed. Matter would have been ripped apart before it could clump together and ignite the elements needed for planets and life. The universe would be a thin, cold, empty soup. On the other hand, if dark energy were much weaker or even negative, gravity would have won the tug of war completely. The universe would have collapsed back into a big crunch long before the billions of years needed for stars to live and die, for planets to cool, and for complex life to evolve. We live in a Goldilocks universe. The value of dark energy, this force that makes up nearly 70% of the cosmos, just happens to fall within the razor-thin range that allows stars, galaxies, planets, and us to exist. It's so precisely tuned that physicists have called its predicted value the worst theoretical prediction in the history of physics, because our theories suggest it should be about 120 orders of magnitude larger than it is. So, the arrow of causality might not point from your heartbeat to the cosmos. It might point from the cosmos to your heartbeat. The universe doesn't have the properties it does because you are alive. You are alive because the universe has the properties that it does. The expansion isn't a consequence of life, it's a prerequisite for it. This flips our what if on its head. Our existence doesn't cause the finely tuned expansion. Our existence is evidence of it. We are the proof. The fact that a fragile, complex process like life can exist at all tells us something fundamental about the cosmos we inhabit. It connects us to the universe not through power, but through inheritance. You are not a cosmic engine, pushing the gears of spacetime. You are a cosmic heir, the beneficiary of a universe that, for reasons we don't yet grasp, is strangely hospitable to life. And that inheritance comes with a strange and beautiful legacy. The legacy of a pulse. Let's go back, one last time, to your heartbeat. We've established that its energy is cosmically insignificant. A single joule of energy is a whisper in a hurricane. But it is not zero. And in physics, that can make all the difference. When your heart beats, it radiates energy. Photons of heat leave your skin. Tiny pressure waves move through the air. A minuscule ripple in space-time is created by the motion of your blood. These pulses of energy, photons, sound, gravitational waves, travel outwards, away from you, at the speed of light. They will pass the moon in just over a second. They will leave our solar system in a few hours. In 100,000 years, they'll have crossed the entire Milky Way. Long after you are gone, long after Earth has been swallowed by the sun, long after our sun has become a cold, dead cinder, those tiny packets of energy from your life will still be traveling. They will cross the vast, expanding emptiness between galaxies. They will be stretched by the expansion of space itself, their wavelengths getting longer, their energy diminishing, but they will not stop. The energy from a single one of your heartbeats will travel for billions, perhaps trillions of years, a final, faint testament that you were here. It will become a permanent, ever-expanding feature of the cosmos. Now, think of that hum of the biosphere again. All the heartbeats, all the breaths, all the motions of every living thing that has ever been. Every single one has sent its own signal into the void. The collective pulse of all life is an expanding shell of information and energy, forever woven into the structure of spacetime. So, while your direct impact is infinitesimally small, your existence leaves a permanent mark. You aren't just living in the universe, you are imprinting yourself on it. Your very aliveness is being written into the fabric of the cosmos, a message in a bottle thrown into a cosmic ocean that will travel for eternity. This is the cosmic boomerang. We start with the intimate feeling of a heartbeat. We travel to the edge of the cosmos and confront our own insignificance. And then, we return with a new perspective. Our significance isn't measured in the cosmic forces we can command. It's measured in the fact that we are here at all to witness the grandeur. And it's measured in the fact that every moment of our existence sends a signal, however faint, that will never be erased. You are not just a passenger. You are a participant. Your life is being woven into the fabric of space-time, a permanent part of its history, one beat at a time. The story of our universe is one of shocking discoveries that force us to rethink our place in it all. We thought the cosmos was static, then we found it was expanding. We thought the expansion was slowing, then we found it was speeding up. We thought its fate was a cold, empty freeze, and now new hints suggest the story could change all over again. And in the middle of all this cosmic drama, there's us. Tiny, fragile collections of matter on a small rock orbiting an average star. It's easy to feel insignificant, a rounding error in the cosmic equation. But the connection between your life and the universe is real. Not because you are powerful, but because you are a product of its impossible fine-tuning. And every second you exist, you send a part of yourself back out into it. A pulse that will echo into eternity. So, the next time you feel your heartbeat, that steady, quiet rhythm in your chest, remember what it is. It's not just a muscle pumping blood. It's the sound of you sending a message to the cosmos. A permanent signature of your brief, improbable, and beautiful existence. What a strange and wonderful thing that is. This is one of those ideas that sits right on the edge of hard science and philosophical wonder. The numbers say our direct impact is negligible, but the fact that we're even here to ask the question is profound. What do you think? Is the anthropic principle a satisfying explanation for our Goldilocks universe? Or does it feel like a cop-out? And what does it mean to you that a piece of your existence, the energy of your life, will travel through the cosmos forever? Let me know your thoughts in the comments below. These are the kinds of questions we love to explore. If you enjoyed this journey from your own heart to the edge of space and time, please consider subscribing and turning on notifications. We have a lot more of the cosmos to explore together. The glitch in the cosmos that allows you to exist. There is a lottery, not a familiar one. The winning number isn't 6 digits long, it is 1 billion digits long. The chance of winning is so small that, for all practical purposes, it is 0. And yet, the next day, you find you have won. Every digit matches. After the initial feeling passes, you would be left with 2 possibilities. Either you are the luckiest person to have ever existed, by a margin so vast it is difficult to comprehend. Or, the game was fixed. This is not a thought experiment. It is the situation you find yourself in right now. Your body, the world around you, the stars in the sky. They are all the result of a cosmic lottery that should have been impossible to win. The universe we live in appears to be balanced on a razor's edge, a quiet glitch in an otherwise hostile infinity. If a single, fundamental property of our cosmos were changed by even a fraction, the whole thing would cease to exist in any recognizable form. No stars, no planets, no you. We seem to be the beneficiaries of a cosmic game that was arranged in our favor from the very first moment. The question is, why? The unwinnable lottery. The idea that our universe is fine-tuned for life is one of the most quiet and profound observations in science. It suggests that the basic numbers of the cosmos are set to values that fall within an extraordinarily narrow range, a range that permits the emergence of complex things, like stars, planets, and eventually, living beings. If you stray even slightly outside this life-permitting sliver, the universe becomes sterile, empty, and dead. Think of the universe as a machine governed by a control panel with many dials. Each dial represents a fundamental constant of nature, a number we can measure, but whose value we cannot predict from theory. These are the raw ingredients of reality: the strength of gravity, the speed of light, the mass of an electron. They simply are. And yet, their values appear to be part of a quiet conspiracy. Let's begin with gravity. It feels strong, capable of holding us to the Earth and binding galaxies together. But in the larger scheme of forces, it is almost invisibly weak, about 10 to the power of 36 times weaker than the electromagnetic force holding your atoms together. If gravity were just a little stronger, stars would burn through their fuel millions of times faster, giving life no chance to evolve. A slightly stronger gravity would have also caused the universe to collapse back in on itself shortly after its birth, long before the first galaxy could form. Now, let's turn the dial the other way. If gravity were slightly weaker, the first clouds of gas in the early universe would have spread out too quickly. Matter would never have gathered to form the first stars and galaxies. The cosmos would be a thin, cold soup of isolated atoms. No structures, no complexity, no life. The balance was essential. But it's not just gravity. Consider the electromagnetic force, which governs light and the structure of atoms. If you were to increase its strength by a small amount, the repulsion between protons in an atom's nucleus would become too great. Complex atoms would be unstable. If you were to decrease it, the bonds holding atoms together would be too weak. The chemistry we know would not work. The story becomes more specific and more strange. A neutron is just a tiny bit heavier than a proton, about 0.14% heavier. This slight difference is crucial. Because it is heavier, a free neutron decays into a proton. This allowed for a universe made mostly of hydrogen, the fuel of stars. If the neutron were just 0.1% lighter than a proton, then protons would have decayed into neutrons. In such a universe, there would be no hydrogen, no long-lived stars, no heat, no light, and no chance for life. Each of these dials is tuned with a precision that is difficult to understand. It is not like winning a lottery with a 1 in a million chance. It is like guessing a number with hundreds of decimal places correctly. To many physicists, this looks less like a random coincidence and more like a setup. The universe seems to have been carefully calibrated to allow for observers to one day emerge within it. A glitch in the expected randomness of the cosmos. A glitch that allows you to exist. The carbon coincidence. If the general settings of the universe seem strangely tailored for life, there is one detail so specific that it caused the scientist who found it to question his own beliefs. It involves a single atom, essential for life as we know it. Carbon. To understand this, we have to travel back in time, into the hearts of the first giant stars. The Big Bang produced almost only hydrogen and helium. Every other element, the oxygen you breathe, the calcium in your bones, the carbon that forms your cells, was forged inside stars. This process is called stellar nucleosynthesis. Stars spend most of their lives fusing hydrogen into helium. When the hydrogen runs out, the core heats up, allowing helium to fuse into heavier elements. The first step is for two helium nuclei to combine, forming beryllium-8. Here is the first problem. Beryllium-8 is wildly unstable. It decays back into two helium nuclei in a 10 millionth of a billionth of a second. For a heavier element to be made, a third helium nucleus must strike the beryllium-8 in that infinitesimal window of time. This is the only way to produce carbon-12. In the early 1950s, the astrophysicist Fred Hoyle was trying to understand how stars could create so much carbon. His calculations showed that this process, called the triple alpha process, should be extremely rare. It would be like trying to get 3 billiard balls, shot randomly, to all collide at the exact same point at the same time. The process was so inefficient that, according to the physics of the time, the universe should have almost no carbon at all. But Hoyle reasoned backward. He said, in effect, we exist. We are carbon-based. Therefore, there must be a way to make lots of carbon. He made an extraordinary prediction. For the process to work, there must be a resonance in the carbon-12 nucleus. A resonance is a specific, excited energy state. Hoyle predicted that carbon-12 must have an excited state at a very precise energy level, around 7.7 megaelectron volts, MeV. If this resonance existed, it would act like a cheat code. The combined energy of the beryllium-8 and the third helium nucleus would perfectly match this excited state, and the probability of the reaction happening would skyrocket. Hoyle, a staunch atheist, was so convinced that he asked a team of experimental physicists to search for this energy level. They were skeptical. No such resonance had ever been seen. But they conducted the experiment. They found the resonance at 7.65 MeV, almost exactly where Hoyle said it had to be. The discovery was profound, but there is another layer. For carbon to be useful, it must not only be created, it must also survive. Once carbon-12 is formed, it's possible for it to capture another helium nucleus and become oxygen-16. If there were a similar resonance in the oxygen nucleus, almost all the carbon would have been immediately converted into oxygen. No carbon, no life. As it turns out, there is a resonance in oxygen-16, but it is just below the required energy level, making the conversion of carbon to oxygen inefficient. So we have a double coincidence. A perfectly placed resonance in carbon that allows it to be made, and a conveniently misplaced resonance in oxygen that allows it to stick around. Tweak the strength of the strong nuclear force by as little as 0.5%, and these levels shift, shutting down carbon production. Fred Hoyle himself later wrote, "A common-sense interpretation of the facts suggests that a superintellect has monkeyed with physics, as well as with chemistry and biology." It seemed less like a random outcome and more like the universe wanted to create carbon. The biggest blunder in physics, that wasn't. If the tuning of forces and particles feels like a puzzle, there is one number in cosmology that takes this mystery to a different level. It revolves around a concept that Albert Einstein once called his biggest blunder, a ghost in his equations that returned to physics a century later, the cosmological constant. The story begins in 1917. Einstein had just formulated his theory of general relativity. But his equations predicted that the universe must either be expanding or contracting. A static, unchanging universe, which was the belief at the time, was impossible. To fix this, Einstein introduced a mathematical fudge factor into his equations, which he called the cosmological constant. It acted as a kind of repulsive force, a pressure in space itself, that would counteract gravity and hold the universe still. A decade later, the astronomer Edwin Hubble discovered that the universe was not static. Distant galaxies were moving away from us. The universe was expanding. Einstein reportedly regretted his invention, calling it his greatest blunder. For decades, the cosmological constant was mostly forgotten. Then, in 1998, the story took a quiet turn. Two teams of astronomers found that the expansion of the universe was not slowing down. It was accelerating. Something was pushing space apart. Suddenly, Einstein's blunder did not look like a blunder. This mysterious force, now called dark energy, behaved exactly like his cosmological constant. It seemed there was an energy woven into the very vacuum of empty space. And this is where the mystery deepens. According to quantum field theory, empty space should be a seething soup of virtual particles that pop in and out of existence. This quantum fizz should give the vacuum of space an enormous amount of energy. So, physicists tried to calculate how much vacuum energy there should be. The number they came up with was unimaginably colossal. If the cosmological constant truly had this value, the repulsive force would have been so powerful that the universe would have blown itself apart in its first moments. No galaxies, no stars, no planets. Just an infinitely expanding, empty void. But that is not what we see. The observed value of the cosmological constant is tiny. It is just enough to gently push galaxies apart over billions of years. When you compare the theoretically predicted value with the observed value, the predicted value is larger by a factor of 1 followed by 120 zeros. This is a number larger than all the atoms in the known universe. It is the most profound disconnect between theory and observation in the history of science. It is like calculating that a grain of sand should have the mass of 1 trillion galaxies, and then finding it weighs what a grain of sand should. For the universe to exist as it does, this gargantuan predicted energy must have been cancelled out by some other, unknown effect to a precision of 120 decimal places, leaving just a tiny remnant. Physics has no answer. The value of this one constant seems to have been tuned with an almost supernatural precision. It is the grandest glitch of them all, a number so finely balanced it suggests either our understanding of physics is deeply incomplete, or there is something very strange about the nature of reality itself. The anthropic principle, a different way of seeing. So we are faced with a universe that appears fine-tuned for our existence. How do we begin to explain this? Is it a sign of incredible luck, a cosmic mystery, or something else? This is where a quiet and often misunderstood idea enters the conversation. Some see it as a profound insight, and others as a philosophical sidestep. It is called the anthropic principle. In its most straightforward form, it is known as the weak anthropic principle, WAP, asterisk. The WAP states that the observed values of all physical quantities are not equally likely. They are constrained by the requirement that we must be here to observe them. In simpler terms, our location in the universe, in space and time, must be compatible with our existence as observers. This can sound like a statement that is true by definition. Of course, the universe has to be compatible with our existence, otherwise we would not be here. But while it sounds obvious, it has quiet implications. Imagine you wake up on a boat in the middle of a vast ocean. You might ask, why am I on a boat that floats? Why not one at the bottom of the sea? The answer is simple. If you were on a boat at the bottom of the sea, you would not be alive to ask the question. Your observation of being on a floating boat is a selection effect. You are filtering all possible locations by the fact of your own survival. The weak anthropic principle applies this same logic to the cosmos. Instead of asking, why is the universe so incredibly old, around 13.8 billion years? The anthropic answer is, because we can only find ourselves in a universe old enough to have created us. The elements for life, like carbon and oxygen, had to be forged in stars, which then had to live and die to scatter those elements into space. This process takes billions of years. We should not be surprised to find ourselves observing a universe that is many billions of years old, because a younger one could not have formed us. The same logic applies to the universe's size. A large universe is a necessary consequence of an old universe. Because it is expanding, for it to reach an age of nearly 14 billion years, it must have grown to be many billions of light years across. A small, cozy universe would also be a young universe, far too young for us to exist within it. Many have criticized this reasoning. They argue that it does not make testable predictions and seems to explain things away by saying, it had to be this way. It feels like circular logic. Science, they argue, should seek a deeper reason for why the constants have their values. However, defenders of the principle see it as an essential tool. It reminds us that our own existence is a piece of data, and that data creates a powerful bias in what we observe. The principle doesn't explain how the constants got their values, but it does explain why we observe the values that we do. We shouldn't be shocked to find ourselves in a hospitable universe, just as we shouldn't be shocked to find life on Earth but not on the surface of the Sun. The fact that we are observers filters out all the uninhabitable options. If this kind of calm exploration into the quiet corners of science helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Now, where were we? The anthropic principle gives us a new way to think, but it does not fully solve the mystery. It leads us to two truly radical possibilities. The glitch in the code. Multiverse or meaning? The weak anthropic principle tells us that we should not be surprised to find our universe fine-tuned, because we could only exist in such a place. But this still leaves the fundamental question: how did it get these properties? The principle itself does not provide the mechanism. This final question leads us down two very different paths. The first, and the one that has gained the most traction in the scientific community, is the asterisk multiverse hypothesis. This idea proposes that our universe is not the only one. Instead, it is just one small bubble in a vast cosmic foam of other universes. In this model, each universe could be born with its own unique set of physical laws and constants. Imagine a cosmic factory that produces universes, but with the settings chosen at random each time. The overwhelming majority of these universes would be sterile. In one, gravity might be so strong that it collapses in a microsecond. In another, atoms might not form at all. In yet another, the cosmological constant might be as huge as our theories predict, blowing the universe apart before anything can happen. These universes would be born and die in darkness, with no one to witness them. But in a vast collection of universes, statistics suggest that every combination will eventually occur. By sheer chance, a few universes will happen to have their dials set to the precise, narrow range that allows for life. Our universe, in this view, is simply one of those lucky ones. We find ourselves in a life-permitting universe for the same reason a lottery winner finds themselves holding the winning ticket. Not because the lottery was rigged for them, but because out of millions of losing tickets, one had to win. What is compelling about this idea is that some of our leading physical theories, like eternal inflation and string theory, seem to predict a multiverse. It is not just an idea pulled from thin air. It is a potential consequence of our deepest theories about reality. The main criticism, however, is a large one. The multiverse is, for now, untestable. By definition, these other universes are disconnected from our own. This leads many to argue that the multiverse is not science, but philosophy, as it cannot be proven false. This leads us to the second path. What if there is only one universe? If we reject the multiverse, we are back where we started, confronted with the quiet improbability of our own existence. If there is only one lottery ticket and it wins, you have to suspect something is going on. One possibility is that there is a deeper physical law we have not yet found. A true theory of everything might one day show that the values of the constants are not random at all, but are mathematically required to be the way they are. In this scenario, the fine-tuning for life would be a genuine coincidence, a fortunate byproduct of an unchangeable set of laws. We are still searching for such a theory. The other possibility, if one assumes a single universe, is the one Fred Hoyle reluctantly pointed towards: the asterisk design interpretation. If the universe is not a statistical inevitability and its constants are not mathematically necessary, then one might conclude that they were intentionally chosen. This interpretation suggests the fine-tuning is evidence of some form of purpose. This is a philosophical stance, not a scientific one, as it invokes a cause that lies outside of nature. Science cannot prove or disprove it, but it is important to acknowledge that the fine-tuning problem is what leads many people to this conclusion. The apparent glitch that allows us to exist is seen not as an error, but as a feature. And so we are left on a quiet precipice, looking at a set of radical and unproven possibilities. The observer's paradox. We began with a simple observation: our universe appears to have won an unwinnable lottery. From the precise strength of gravity to the delicate energy resonance inside a carbon atom, the cosmos seems built on a series of quiet coincidences. A glitch in the code of reality that makes our existence possible. In our search for an answer, we encountered the anthropic principle. It suggests we should not be surprised to find ourselves in a life-friendly universe, because we simply could not exist anywhere else. Our existence acts as a selection filter, ensuring that we only ever see a cosmos that is compatible with us. This principle, however, does not explain how things came to be this way. It points us toward the multiverse, the idea that our universe is just one of countless others, and we are living in a rare one where the conditions for life happen to be right. Or, if our universe is all there is, it leaves us with an unexplained improbability, which some see as a sign of deeper laws yet to be found, and others as evidence of purpose. What we are left with is an observer's paradox. The universe does not seem to have been made for us. And yet, we can only be in a universe that looks as though it were made for us. This is the glitch. The fact that you are here, thinking these thoughts, a conscious being made of stardust, is the most powerful piece of data we have. Perhaps the most astonishing fact is not the fine-tuning itself, but that the universe has produced a part of itself, that is capable of looking back and noticing. A collection of atoms forged in long-dead stars can now build telescopes, write equations, and ponder the very improbability of its own being. We are the glitch in the cosmos that allows the cosmos to be known. And that, in itself, might be the most meaningful part of the puzzle. The cosmic secret you'll understand before you sleep. To look up at the night sky is to feel a particular kind of solitude. It is a sensation woven into human history, a feeling of being a small, distinct observer in a silent and impossibly vast cosmos. We exist beneath a tapestry of stars, a sprawling, glittering arrangement that stretches into infinity, and it is difficult not to feel small. The silence between those stars can feel absolute, a deep and ancient quiet that seems to hold no answers, only more questions. One can feel like a single point of awareness in a dark, endless cathedral, a brief spark in an ocean of cosmic indifference. But what if that silence is not empty? What if the feeling of separation, of being a lonely witness, is a misunderstanding? A trick of perspective? Tonight, we will explore a cosmic secret. A strange and beautiful connection whispered between the stars and the mind. It is a story that begins in the loneliest void and ends with a feeling of profound belonging. This is a calm exploration into a great mystery, arriving at a clear and comforting answer. There is nothing to do but listen, and allow the mind to wander out into the great, beautiful darkness. The silent universe and the first whisper. The journey begins with an appreciation for scale. It starts with our own world, a familiar sphere of blue and white. Now, pull back, see the moon, our silent companion, held in its orbit by patient gravity. Pull back further. Watch as the Earth shrinks, becoming another point of light in the celestial dance of our solar system. The Sun, a roaring furnace that once seemed so mighty, is now just one star among billions. Our entire solar system becomes a tiny, almost insignificant speck within a grand spiral arm of the Milky Way galaxy. And the Milky Way itself, with its hundreds of billions of suns, is just one galaxy among at least 2 trillion others scattered like dust across the observable universe. 2 trillion galaxies, each one a universe of stars, planets, and possibilities. The light from the most distant of these has traveled for nearly 13.8 billion years to reach us, a journey across an almost unimaginable expanse of space and time. To look at that light is to see a ghost from the dawn of creation. Confronted with this scale, this almost violent immensity, the feeling of being small is not just understandable, it is nearly inevitable. It is easy to believe that we are an accident. A brief, improbable flicker of life on a forgotten rock, circling a nondescript star, in an unexceptional corner of an indifferent cosmos. Our thoughts, our feelings, our entire existence can seem utterly meaningless against such a backdrop. We are spectators to a cosmic play of such grandeur that our own role feels insignificant. We are separate, we are observers. And yet, it is here, in this moment of cosmic loneliness, that the first hint of a different story emerges. It comes not from the giant telescopes that gaze into deep space, but from the microscopes that peer into the very heart of matter. It comes from a realm so small it defies all everyday intuition, a world where the rules of our solid, predictable reality break down completely. This is the quantum realm. And it is here that we find the first clue that the relationship between the observer and the observed, between consciousness and the cosmos, is far stranger and more intimate than we ever imagined. The first whisper suggests that the act of looking, the simple act of observation, might not be a passive event at all. It might be a creative one. To understand this, we must leave the comfortable world of stars and planets behind and venture into a place of pure possibility, a world of ghosts and waves, where reality itself seems to be waiting for a decision. We are about to journey into the strange world of quantum mechanics, and it is here that our search for connection truly begins. The quantum ghost, a world of possibility. Imagine a quiet laboratory, late at night. The only sound is the low hum of equipment. In the center of the room is a simple apparatus, a device that can fire a single particle, an electron, like a tiny marble. In front of it is a solid barrier with two thin, vertical slits, side by side like two open doorways. Beyond the barrier is a screen that will light up wherever an electron hits it. This is the stage for the most famous and unsettling experiment in all of physics, the double-slit experiment. First, one slit is covered, leaving only a single doorway open. As the electrons are fired, one by one, the pattern on the screen is exactly what intuition would predict. The electrons pass through the open slit and form a single, bright band directly behind it. It is simple, predictable, and comforting in its logic. Now, the second slit is uncovered. Both doorways are open. We continue to fire the electrons, one by one. Our intuition, based on a world of solid objects, tells us what should happen. Some electrons will go through the left slit, some through the right, and two distinct bands will form on the screen. But that is not what happens. As the electrons strike the screen, one after another, a pattern begins to emerge. It is not two bands. It is many bands, a series of bright and dark stripes spread across the screen. This is an interference pattern, the kind created when two waves overlap. Where their crests meet, they reinforce each other. Where a crest meets a trough, they cancel each other out. This should be impossible. We were firing single particles. A single electron, traveling from the gun to the screen, should not be able to create a wave pattern. The only way this interference can exist is if the electron did not go through one slit or the other. It had to have gone through both slits at the same time. Let that sink in for a moment. The single electron, a fundamental particle, left the gun as a single entity. But when faced with a choice, it did not choose. It became a wave of possibility, a ghostly wave, that flowed through both slits simultaneously. It then interfered with itself, its own wave of potential passing through both openings, and only then did it rematerialize as a particle to strike a single point on the screen. The position it lands in is determined by the ghostly dance of its own interfering possibilities. It is as if each electron, before it settles into reality, is a smear of pure potential, exploring every available path at once. This is a core tenet of quantum mechanics, known as superposition. This result is so bizarre that physicists themselves were deeply unsettled. They thought, surely, we can find out which slit it really goes through. And this is where the cosmic secret begins to get personal. This is where the observer steps onto the stage. The watcher in the dark. The physicists in our imaginary laboratory are puzzled. They want to know the secret of the electron. They decide to peek. They place a tiny detector next to one of the slits. All it does is register whether an electron passes through that specific slit. It won't stop the electron, it will just watch. The experiment begins again. The detector is in place, ready to tell us which path each electron takes. For each electron fired, our detector tells us definitively which path it took. There is no more ambiguity. We have solved the mystery. But as we look at the screen behind the slits, a cold, strange feeling begins to dawn. The pattern has changed. The beautiful, mysterious series of many stripes, the interference pattern, is gone. In its place are just two simple bands, one behind each slit. The electrons are behaving like particles again. The magic is gone. The ghost in the machine has fled. The mere act of watching, the act of measuring which path the electron took, forced it to make a choice. It collapsed the electron out of its ghostly wave state of superposition and made it a single, definite particle with a single, definite path. This is the famous and often misunderstood observer effect. Reality, at its most fundamental level, seems to change depending on whether or not it is being watched. Now, this is the point where the story often takes a mystical turn, suggesting human consciousness itself is the magical ingredient. But the truth, as revealed by decades of careful experimentation, is both more subtle and, in its own way, more profound. The observer in the double-slit experiment does not have to be a person. The key is not the act of a mind knowing, but the act of a physical system interacting. At the Weizmann Institute of Science, researchers performed an elegant version of this experiment where their observer was a sophisticated electronic detector, a mindless machine. They found that the very presence of this detector caused the interference pattern to degrade. When they turned its sensitivity down, so it only had a vague idea of which path was taken, some of the wave-like pattern returned. When they turned its sensitivity all the way up, getting a definitive yes or no for each particle, the interference vanished completely. The experiment revealed that the more which path information is gathered, the more the particle-like behavior dominates. To see which slit the electron goes through, you have to interact with it. And the electron is so delicate in its wave-like state that this tiny interaction is enough to disturb it. It's like trying to find the location of a tiny ripple in a pond by throwing a bowling ball at it. The act of measuring irrevocably changes the thing you are trying to measure. So, it is not our consciousness that collapses the wave. It is the inescapable physical requirement of measurement. Any interaction that distinguishes one path from another is enough to destroy the delicate superposition. But this discovery does not remove the mystery. It deepens it. It leaves us with an even bigger question. If a particle exists as a smear of possibilities until it is measured, and measurement is just an interaction, what counts as a measurement? Where is the line between the quantum world of possibilities and the solid, classical world we experience? This is known as the measurement problem and it is one of the deepest and most fiercely debated puzzles in all of science. The great cosmic headache, the measurement problem. Quantum mechanics seems to operate with two conflicting sets of rules. On one hand, there is the beautiful, predictable mathematics of the Schrödinger equation. This describes how a quantum system evolves over time when left alone. According to this rule, the electron's wave of possibility spreads out in a perfectly deterministic way. There are no sudden jumps. On the other hand, there is the abrupt and probabilistic rule of measurement. The moment we measure the system, the Schrödinger equation is discarded. The smooth wave of possibilities instantly collapses, and the particle appears in one single, definite place, chosen at random. This clash is the heart of the measurement problem. Why are there two different rules? What constitutes an observation to make the universe switch from the smooth waltz of the wave to the sudden snap of the particle? A century after its inception, physicists are still deeply divided on what it all means. Let's drift through a few of the leading ideas, not to find a final answer, but to appreciate the sheer strangeness of the possibilities. The oldest explanation is the Copenhagen interpretation championed by pioneers like Niels Bohr. In its simplest form, it posits a fundamental division between the quantum world and our classical world. The quantum realm only solidifies into a definite reality when a measurement is made by a classical apparatus. It is pragmatic and works for making predictions, but it's deeply unsatisfying, as it doesn't explain how or why the collapse happens. Then there is perhaps the most audacious idea in all of science, the many worlds interpretation. Proposed by Hugh Everett, it offers a radical solution: the collapse never happens. The smooth evolution of the Schrödinger equation is the only rule. When you measure the electron, the universe splits. In one universe, you see the electron go through the left slit. In another, parallel universe, a copy of you sees it go through the right. Every quantum measurement causes reality to branch into an array of parallel worlds, with all possible outcomes actually occurring. Other physicists have explored different paths. Objective collapse models * propose that the collapse is a real, physical process, a tiny, inherent randomness in nature that causes wave functions to spontaneously collapse on their own, with the probability increasing with the size of the system. This would explain why we never see quantum weirdness in large objects. A more modern and mainstream piece of the puzzle is an idea called * decoherence. This concept explains how quantum weirdness seems to fade away. No quantum system is ever truly isolated. It is constantly interacting with its environment, bumping into air molecules, absorbing stray photons. Each tiny interaction is a form of measurement that leaks the quantum information out into the wider world, destroying the superposition. Decoherence beautifully bridges the quantum and classical worlds, but many argue it doesn't fully solve the measurement problem. It explains why we don't see interference between different outcomes, but it doesn't explain why we experience only one of those outcomes in the end. So, after a century of brilliant work, the debate rages on. We are left with this strange situation. The act of measurement is fundamental to our reality, yet we have no consensus on what a measurement actually is. It leaves a tantalizing, almost mystical door open. If reality is a field of possibilities until an interaction forces a choice, could the universe itself be influenced by the sum total of all the observations happening within it? From the atom to the stars. Let us pull our focus back now. Gently, let's zoom out from the strange, flickering world of a single electron. Pull back from the lab, from the Earth, and drift back out into the cosmic dark. We return, but we bring our quantum secret with us. We now know that the universe, on its smallest scales, is a shimmering, undecided sea of potential. Reality is not a fixed thing, but a story being written moment by moment, interaction by interaction. And as we float here, in the majestic quiet of deep space, we see that the universe is not static. Galaxies are rushing away from each other. The fabric of spacetime itself is stretching, expanding, driven by a mysterious force we call dark energy. It is a speculative, but poetically powerful thought. Could these two truths be connected? Could the countless acts of observation happening throughout the cosmos, not just by humans, but by any system capable of registering information, be contributing to the universe's evolution? If every quantum measurement forces a collapse, could the cumulative effect of trillions upon trillions of collapses every second, across billions of years, have a large-scale cosmic consequence? Could life, in its simple act of witnessing the universe, be subtly influencing its grand trajectory? It's a beautiful thought. It takes the loneliness we felt at the beginning and transforms it. We are no longer just passive onlookers. We become participants. Our awareness becomes a part of the great engine driving reality forward. The universe, in this view, is not just expanding, it is being constantly born from a sea of potential, solidified into reality by the gaze of its own children. This idea would be the ultimate cosmic secret, that the universe needs observers to become real. It is a deeply comforting, deeply empowering thought. But is it true? The comforting truth, the unmoved cosmos. As we hold this beautiful idea, we must also hold onto scientific honesty. The story we have told is a delicate one, weaving together established science and profound philosophical questions. And the scientific answer to our grand question, does consciousness influence cosmic expansion? Is, as of now, a clear and unambiguous no. There is absolutely no evidence that the observer effect, as understood in quantum mechanics, has any influence on the large-scale expansion of the universe. The principles of quantum mechanics are powerful and strange, but their effects are largely confined to the microscopic world. As systems get larger, The process of decoherence washes away the quantum weirdness almost instantly. The universe on the scale of stars and galaxies behaves according to the laws of general relativity, which has been tested and confirmed with breathtaking precision. The expansion of the cosmos is governed by the initial conditions of the Big Bang, the amount of matter and energy in the universe, and the cosmological constant. These forces are utterly indifferent to the quantum drama happening on Earth or any other planet. To put it simply, the quantum jitters of a single particle in a lab do not ripple outwards to nudge a galaxy. And here, at the end of our journey, one might feel a pang of disappointment. Have we come all this way, from the lonely void to the heart of the atom and back, only to arrive at the same conclusion? That we are, after all, just insignificant observers? No, because the real cosmic secret is not what we thought it was. It is something far more intimate. The real cosmic secret. The secret is not that we change the universe by looking at it. The secret is that we are the universe, looking at itself. You are not a separate entity that happened to emerge on a speck of dust. You are a part of the cosmos. The iron in your blood, the calcium in your bones, the oxygen you breathe, every atom in your body was forged in the heart of a dying star, billions of years ago. You are made of stardust. The universe is not something out there. You are the universe, experiencing itself in a localized and exquisitely complex form. The observer effect isn't a sign of magical powers. It's a sign that the fundamental division we make between ourselves and the world is an illusion. You are not a spectator watching a separate event. You are one part of a quantum system interacting with another. You are part of the whole. The profound sense of loneliness one feels when looking at the night sky comes from the illusion of separation. But the truth is, you are not separate. You are as much a part of the cosmos as a star, a nebula, or a galaxy. Through your eyes, the universe contemplates its own grandeur. Through your mind, it asks questions about its own existence. Through your heart, it experiences wonder. That feeling of connection is not something one needs to find. It is something one need only recognize. You are not a flicker of consciousness in a dead and silent void. You are the cosmos, awake and dreaming. So as you prepare to drift off to sleep, let go of the feeling of being a small, separate self. You are not alone in the cosmos. You are the cosmos, and your consciousness is one of the ways it has come to reflect on its own glory. The cosmic secret you can understand before you sleep is this: you are home. You have always been home. A slow story of the universe's final night. There is a story that unfolds not in days or centuries, but across a timescale that dissolves mountains and evaporates stars. It has no heroes or monsters in the familiar sense. It is written in the language of physics, a quiet, inevitable narrative that stretches to the very end of time. This is a journey to the universe's final night. We live under a sky filled with light. For millennia, that light has been a source of wonder, a map for navigation, and a reminder of a vast, connected cosmos. But this display, this brilliant age of stars and galaxies, is temporary. It has an expiration date. This is not a story of a sudden end, a cosmic cataclysm. It is the story of a slow, fading silence. The story of heat death. It is a journey that may sound unsettling, but in its vastness, there is a profound sense of perspective to be found. It is the final chapter, where the last lights go out and the cosmos grows still. So, let us begin this calm exploration into the long good night. The story begins not with a sudden event, but with a persistent force woven into the fabric of space itself. We call it dark energy, and it is the dominant component of our universe, making up nearly 70% of its total energy density. For the first several billion years after the Big Bang, gravity was the primary architect. It pulled matter together, forming the first stars and shaping the great clusters of galaxies. Gravity built a universe of cosmic neighborhoods. But dark energy worked against it. Unlike gravity, which weakens as objects move apart, the influence of dark energy appears to remain constant. For billions of years, gravity held the advantage. But as the universe expanded, the density of matter thinned, and gravity's influence began to fade. Around 6 billion years ago, a tipping point was reached. The relentless push of dark energy overpowered the weakening pull of gravity, and the expansion of the universe began to accelerate. This was not a minor adjustment. It was a fundamental shift in the destiny of the cosmos. It committed the universe to a future of irreversible separation. This is not like an object speeding up. It is space itself that is stretching, carrying galaxies away from each other at an ever-increasing rate. This acceleration is the engine of our story, the mechanism that will slowly dismantle the interconnected universe we know. It is the beginning of the end. The vanishing galaxies. Right now, our most powerful telescopes can observe a universe filled with perhaps 2 trillion galaxies. 2 trillion islands of light, some so distant their light has traveled for over 13 billion years to reach us. But the edge of what we can see is not a physical wall. It is a horizon, a point beyond which light has not yet had time to arrive. We know the universe extends far beyond this observable bubble. But the accelerating expansion is changing the nature of this horizon. The space between us and the most distant galaxies is stretching so fast that it carries them away from us faster than the speed of light. This does not violate relativity. Nothing is moving through space at that speed. Rather, the space itself is expanding, and the galaxies are carried with it. It creates a situation where the light from those distant galaxies, traveling toward us at light speed, can no longer overcome the expansion of the space it must cross. This process has already begun. A vast number of the galaxies we can see in our telescopes are, in reality, already unreachable. We can see their ancient light, but we could never travel to them, even at the speed of light. They have crossed a causal boundary, a point of no return. Now, let's move forward in time. In about 100 million years, a future observer would see a dramatically emptier sky. Every galaxy outside our own local supercluster will have been carried beyond the cosmic horizon, their light redshifted into undetectability. They will have vanished. Fast forward again, to 150 billion years from now. By this point, the expansion will have isolated our own local group, our small, gravitationally bound cluster of galaxies, including Andromeda. Every other galaxy will be gone, causally disconnected from us forever. Their last photons will have arrived, stretched into faint whispers, and then, there will be nothing. This tells an important story. A civilization born in this era would look into the cosmos and see only the stars of its own merged galaxy, adrift in a seemingly endless void. They would have no evidence that a universe of trillions of other galaxies had ever existed. Their cosmology would be one of solitude. This is the first stage of the universe's final night, the slow drawing of the curtains, leaving only our own local island of light in an immense darkness. The long twilight of the stars. For a very long time, this isolated island, a great merged galaxy sometimes called Milkomeda, will remain a vibrant place. The collision of our Milky Way and Andromeda, beginning in about 4.5 billion years, will trigger a final, magnificent burst of star formation. For a while, the sky will be filled with new light. But this is a final flourish. The raw material for making stars, the vast clouds of hydrogen gas, is a finite resource. Each new star locks away a portion of this material. Even when massive stars die and return some elements to the cosmos, much of that material remains locked away in their remnants. The universe is steadily using up its fuel. The peak of star formation is long past, having occurred some 11 billion years ago. Now we journey forward, deep into the stelliferous era, the age of stars, to watch its slow decline. 1 trillion years from now, star formation has almost completely stopped. The gas clouds have been used up or are too thin for gravity to gather. The massive, brilliant blue stars are long gone. Sun-like stars have faded into cooling white dwarfs. Only the most frugal and long-lived stars remain. These are the red dwarfs. Small and dim, they consume their fuel with extreme patience, capable of living for trillions of years. For an immense stretch of time, these will be the only lights left burning in the universe. The sky of this future would be a deep black, punctuated only by the faint, ruddy glow of these ancient embers. But even their time is finite. One by one, the last of the red dwarfs will exhaust their fuel. They are too small to erupt as supernovae. They will simply fade, cooling into inert black dwarfs, cold cinders of dead matter radiating no light or heat. By 120 trillion years in the future, the last star in the universe will go out. The result is a universe that has fallen dark. The stelliferous era is over. The cosmos is now a silent graveyard of stellar remnants, white dwarfs, neutron stars, and black holes, all drifting in an eternal, starless night. The age of light has ended. The universe now enters the degenerate era, and in this epoch, the very substance of matter will begin to unravel. The slow decay of everything. The universe is now dark and silent. The only significant objects left are the degenerate corpses of stars, all slowly radiating away their last heat, approaching absolute zero. Over quadrillions of years, planets will spiral into their dead parent stars. The galaxies themselves will dissolve, as gravitational encounters fling most of their stellar remnants into the intergalactic void, with the rest falling into the supermassive black hole at the center. But a far more fundamental process may be at work. According to some grand unified theories, the protons that form the nucleus of every atom are not perfectly stable. They may have an incredibly long, but finite, lifespan. This idea of proton decay has never been observed, and if it happens, its timescale is almost impossibly long. A half-life greater than 10 to the power of 34 years. But in the deep future we are now exploring, the improbable becomes inevitable. If protons do decay, they will spontaneously transform into lighter particles, releasing a tiny amount of energy. Matter as we know it can be unmade. Picture a white dwarf, a diamond the size of the Earth, floating in the darkness. For trillions of years, it has been stable. But now, deep inside it, its atoms begin to dissolve. One by one, at an achingly slow rate, its protons decay. Over these unimaginable timescales, all familiar matter will disintegrate. The white dwarfs, neutron stars, and frozen planets will evaporate into a thin mist of radiation and elementary particles. This is not an explosion. It is the most patient demolition imaginable. By the year 10 to the power of 50, the process will be largely complete. All the intricate structures that once defined the cosmos will have been erased. The universe will have become a thin, featureless soup of scattered particles. But one type of object remains, a final repository of structure that has so far resisted decay: black holes. They are the last act of our story. The evaporation of the titans. We have reached the black hole era. All conventional matter has decayed. The only macroscopic objects left are black holes, the gravitational ghosts of former stars and galaxies. It was once thought they were eternal. But in 1974, Stephen Hawking showed that, due to quantum effects at their event horizons, black holes are not completely black. They emit a faint thermal glow, now known as Hawking radiation. The process is often explained through the behavior of virtual particles near the event horizon. Normally, pairs of particles and antiparticles pop into existence and immediately annihilate each other. But if a pair appears at the edge of a black hole, one can fall in while the other escapes. To a distant observer, it looks as though the black hole has emitted a particle. Because of the conservation of energy, this radiation must come from the mass of the black hole itself. The black hole slowly loses mass. It evaporates. This process is indescribably slow. A black hole with the mass of our Sun would take around 10 to the power of 67 years to evaporate. A supermassive black hole could take up to 10 to the power of 100 years, a Google, to disappear. That number is so large it dwarfs the number of atoms in the entire observable universe. For these eons, the universe is a quiet kingdom ruled by these slowly dying titans. As a black hole loses mass, it gets hotter and radiates faster. In its final moments, the evaporation accelerates catastrophically. In the last seconds of a life that has spanned a Google years, a black hole will shrink and its temperature will skyrocket, ending in a final, brilliant burst of high-energy gamma rays. After an eternity of darkness, a sudden flash of light. One by one, from the smallest to the most massive, every black hole will meet this end. Around the year 10 to the power of 100, the last and most massive black hole will finally evaporate. Its final burst of radiation will expand and then fade. With that, the last significant event in the history of the universe is over. We have journeyed through a future that is both vast and quiet. We've seen galaxies vanish, stars die, matter dissolve, and black holes evaporate. It's a timeline that stretches the idea of what existence can be. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And I'm curious to know what you think. What part of this final chapter do you find the most striking? Let me know in the comments below. This community is a huge part of what makes these explorations so rewarding. Now, let's return to our story, for its final, quietest chapter. Heat death. What is left? After the last black hole has vanished, what remains? The answer is almost nothing. The universe has reached a state of maximum entropy, what is known as heat death. It is a vast, dark, and unimaginably dilute void, populated only by a thin, cold soup of photons, neutrinos, and other stray particles, the final remnants of everything that ever was. The expansion that began our story is still ongoing, having stretched the cosmos to a scale that is effectively infinite. This state is called heat death, not because it is hot, but because it has reached thermodynamic equilibrium. Entropy, a measure of disorder, has reached its maximum. In the early universe, there were vast differences in temperature and energy density, stars hotter than the space around them. These gradients allow work to be done, complexity to form, and life to exist. Life itself is a process of creating temporary pockets of low entropy by consuming energy. But in the era of heat death, there are no more energy gradients. The temperature is uniform and infinitesimally close to absolute zero. No work can be done. No complexity can arise. Nothing happens. And when nothing happens, time itself loses its conventional meaning. It is an eternal stillness. The final, silent night. There are speculative ideas about a new beginning, such as a random quantum fluctuation that could, in theory, recreate a low-entropy state. But the timescale for such an event is so ludicrously large it makes the lifetime of a black hole seem like an instant. For all practical purposes, the end is final. And so our story concludes, not with a roar, but with a whisper fading into an endless silence. It reminds us that our own existence, all of its struggles, joys, and questions, plays out in a very specific, and very vibrant, chapter of cosmic history. We live in the stelliferous era, the brilliant morning of the cosmos. A time when the sky is full of light and there are still wonders to behold. The universe's final night may be long, but its day was, and still is, magnificent. Our chance to be a part of it, to witness it, and to understand it, is perhaps the most remarkable thing of all. Life doesn't change the universe, it gives it meaning. For nearly 14 billion years, the universe has unfolded, mostly in silence. Stars have been born and have died, in numbers too large to truly imagine. Galaxies, each one a city of light, have drifted and collided in the dark. All of it happening without a single witness. Imagine the scale of it. A cosmic ocean of events, beautiful and violent, playing out in a theater with no audience. The laws of physics have guided this story from the very first moment. Gravity pulled gas into stars. Fusion forged new elements in their cores. And supernovae scattered that dust across the void, seeding the potential for, what? More stars? More silence? What if all of this was simply setting a stage? What if the universe, after an eternity of solitude, was waiting for an eye to finally open and see it? This is the story of how the universe gained a witness, and in doing so, found a new kind of existence. Think of the most beautiful piece of music ever written, its score locked away, never to be performed. Is it truly music if it is never heard? Or a perfectly composed story with no one to read it? It has structure, but does it have a narrative? For billions of years, the universe was this unplayed symphony. A staggering collection of physical events, a relentless churn of cause and effect, but a story told to an empty room. This can create a quiet feeling of unease. We look out at the cosmos and are struck by its seemingly infinite scale and our own smallness. The feeling can be overwhelming, a sense of being adrift in a cold, uncaring vastness. We are, as the astronomer Carl Sagan famously said, a pale blue dot in the great cosmic dark. As physicist Brian Cox has noted, we are physically insignificant. This is a common source of anxiety, a question that has followed anyone who has ever looked up at the night sky and felt truly alone. But what if we have been measuring our worth in the wrong way? What if our value is not in our physical size, but in something else entirely? What if our significance comes not from changing the universe, but from understanding it? This is where our journey begins, a quiet reframing of our place in the cosmos, moving from a story of physical smallness to one of unexpected meaning. The unchanging universe, a grand, indifferent machine. To understand what life brings to the universe, we first have to appreciate the universe as it is. A place governed by vast, impersonal laws. If we zoom out, far beyond our galaxy, to the largest scales, the universe is described by something called the cosmological principle. This idea states that the universe is basically the same everywhere. There are no special places, and no special directions. There is no center. The Big Bang didn't happen at a single point in space. It happened everywhere, as space itself began to expand. You can think of the universe as a loaf of raisin bread dough rising in an oven. As the dough, space, expands, every raisin moves away from every other raisin. From the perspective of any single raisin, it appears to be at the center of the expansion. But in reality, there is no center. This is our universe. We do not live in a special place. This idea is a foundational part of modern cosmology. This expansion is the dominant process in our universe. And for more than 2 decades, we've known that the expansion is getting faster. To explain this, scientists proposed the existence of dark energy, a mysterious pressure pushing the fabric of spacetime apart. Today, our best estimates suggest that dark energy makes up about 70% of everything in the universe. The fate of the cosmos seems to be written in this quiet battle between the inward pull of gravity and the outward push of dark energy. For a long time, the consensus has been that this will lead to a big freeze, where the universe expands forever, becoming colder, darker, and emptier until the last stars burn out. While scientists continue to refine these models, and new ideas are always being explored, the current evidence points toward a long, quiet fading. In this grand equation, driven by gravity, matter, and dark energy, life is a rounding error. The mass of the entire biosphere on Earth is dwarfed by the mass of the universe to a degree that is hard to comprehend. Our collective physical influence on the cosmos is, for all practical purposes, zero. We do not alter the orbits of galaxies. Our existence does not slow or speed up the cosmic expansion. The universe, in its physical operation, is indifferent to us. Its ultimate fate seems to be written in the language of physics, a language that has no word for life. This is the universe as a machine. Magnificent, complex, and utterly impersonal. It functions according to its programming, the laws of physics, without any need for an observer. This is what the physicist Steven Weinberg meant when he said, "The more the universe seems comprehensible, the more it also seems pointless." From this perspective, we are an accident. A fleeting chemical arrangement on a speck of rock, destined to vanish without a trace, leaving the great machine to run on, unseen and unheard. But this is not the end of the story. It is only the setup for a quiet and profound plot twist. The anomaly, the arrival of the witness. For billions of years, the universe was only a collection of facts. The temperature of a star was a physical state. The light of a supernova was just an emission of photons. These events happened, but they weren't about anything. They were missing a crucial dimension: experience. Then, on at least one small planet, something extraordinary occurred. Out of the same raw materials that formed silent stars and empty worlds, a new kind of pattern began to form. Life was born, and with life came the potential for observation. This was not a small change. The universe, which had previously only existed, could now be known. The conditions for this moment seem remarkably specific. This has led to what is known as the fine-tuning argument. Physicists have noted that many of the fundamental constants of nature seem to be balanced on a knife's edge. For instance, the strong nuclear force, which holds atoms together, is just the right strength. If it were slightly stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for stars like our Sun. If it were a little weaker, complex atoms like carbon and oxygen would never have formed at all. Then there is dark energy. If it were much stronger, the universe would have expanded so quickly that gravity could never have formed galaxies or stars. The precision involved has led to a great deal of debate. As physicist Stephen Hawking noted, the remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. This has led to several ideas. One is the multiverse hypothesis, which suggests our universe is just one of many, each with different laws, and we naturally find ourselves in one that can support us. Another is a philosophical tool known as the anthropic principle. The weak version simply states that the conditions we observe must be compatible with our existence, because if they weren't, we wouldn't be here to observe them. It's a form of selection bias. The strong anthropic principle is more speculative. It proposes that the universe, for some reason, must have properties that allow life to develop. This hints that our existence might not be just an accident, but a more fundamental feature of the cosmos. This is where the physicist John Archibald Wheeler introduced a radical idea: the participatory anthropic principle. Wheeler, known for his work on black holes, argued that a universe without an observer might not be a complete universe at all. Drawing from the strange rules of quantum mechanics, he proposed that reality isn't a fixed, objective thing that exists independent of us. Instead, it is a realm of possibilities that become concrete through the act of observation. The most famous example is the double-slit experiment. An unobserved particle behaves like a wave of possibilities. But the moment you measure it, it settles into a single, definite particle in a single place. The act of measurement seems to collapse the cloud of probability into a single, actual reality. Wheeler extended this idea to the entire cosmos. Through a thought experiment called the delayed choice experiment, he argued that a measurement made today helps define the path a photon took billions of years ago. This doesn't mean we change the past. Instead, it suggests that the past has no existence except as it is recorded in the present. Until an observer looks, the universe is a superposition of all possible histories. The act of observation is what solidifies one of those histories into the story of our cosmos. In Wheeler's participatory universe, the observer and the universe are deeply connected. We are, in his words, participators in bringing into being not only the near and here but the far away and long ago. The universe gives birth to observers, and observers, by looking back, give the universe a definite reality. The arrival of a witness, then, is not just a footnote. It is the moment the story itself comes into focus, from a fog of quantum probability into a narrative. Life did not physically alter the expansion of the universe. But it may have done something far more profound. It transformed the universe from a set of physical probabilities into an observed, experienced, and therefore actualized reality. The reframe, giving the universe meaning. We have arrived at the center of our reframing. We began by feeling small in a vast, mechanical universe. We then introduced the anomaly of the observer, a participant who might be necessary to make reality concrete. Now, we can perform the final act, the reframe. Life doesn't physically change the universe, but by observing it, we give it context, significance, and meaning. Meaning is not a physical property. You cannot measure it. Meaning arises from connection and interpretation. The letters, RED, are just ink on a page. They gain meaning only when a mind connects them to the experience of a specific wavelength of light. Without a mind, there is no connection. There is no meaning. For most of its history, the universe was a book written in a language no one could read. The birth of consciousness was the birth of the first reader. Suddenly, physical processes became experiences. ******** 1. Scientific meaning. The universe knowing itself. The most direct way we give the universe meaning is through science. When we realize that the same force that pulls an apple to the ground also holds the moon in orbit, the universe is no longer a collection of separate events. It is a unified system. When we discover that galaxies are moving away from us, the universe is not just a static place, but a dynamic one with a history. Every scientific discovery is an act of translation. We take the raw data of the universe and translate it into the language of understanding. We find the patterns. We write the equations. In doing this, we are serving a quiet but profound purpose. As Carl Sagan said, we are a way for the cosmos to know itself. Think about that statement. We are not separate from the universe. The carbon in our cells and the iron in our blood were forged in the hearts of long-dead stars. We are made of stardust. So when we practice science, it is the universe, through us, becoming self-aware. ***2. Artistic meaning. The universe feeling itself. Meaning is also about feeling and aesthetic experience. When an artist looks at the night sky, they don't just see balls of burning gas. They see the starry night, a swirling vision of the cosmos. They translate a physical reality into an emotional one. Through us, the cold, silent beauty of a nebula is transformed into awe. The violent death of a star becomes a story of tragedy and rebirth. The Voyager Golden Record, launched into space in 1977, is a perfect example of this. On it, we placed images, sounds, and music. It was a deeply meaningful act. It was humanity holding up a mirror to the universe and saying, "This is what you have become." On one small world, your stardust learned to sing. It was an offering of meaning to the silence. ***3. Philosophical meaning. The universe pondering itself. Finally, we give the universe meaning by asking the biggest questions. Why is there something rather than nothing? What is the nature of existence? These are not questions physics can answer on its own. They are questions about physics. A philosopher thinking about the nature of reality is the universe engaged in self-reflection at the highest level. This brings us back to the idea of value. Physicist Brian Cox argues that if we are the only island of meaning in a vast ocean of cosmic indifference, then our existence is unimaginably precious. To destroy this civilization would be to potentially destroy meaning in our entire galactic neighborhood. Our value is not tied to our physical size, but to our ability to be aware. We are the universe's consciousness. The feeling of insignificance is transformed. We are not small and meaningless. We are rare and precious because we are the only part of the system, as far as we know, that can appreciate the whole. Our purpose may not be to physically alter the course of the cosmos. The stars will continue on their paths, and galaxies will collide. Our purpose is to bear witness. To see it, to understand it, and to feel it. We are the storytellers for a universe that cannot speak. We are the eyes for a universe that cannot see. This idea, that we are participants in the universe, not just spectators, is not a settled fact. It's an ongoing conversation, but that's just one way to look at it. And I'm curious what it feels like to you. When you look up at the night sky, what do you see? Feel free to share your own thoughts in the quiet space below. There are no right or wrong answers here. And if this kind of calm exploration into the universe helps you think or unwind, consider subscribing and joining our journey. An island of meaning. Our journey started in a cold, silent universe, a vast machine unfolding across billions of years. We felt the quiet ache of our own physical smallness. But we have reframed that picture. We've seen that the laws of this universe seem remarkably suited for our existence. We've explored the idea that the observer might be an active participant in bringing reality into being. Most importantly, we've redefined our value. Our worth is not in our mass or our physical power. Our worth lies in our minds. In our ability to do science and understand, to create art and feel, and to ask questions and ponder. Life does not change the universe's physical path, but it changes what the universe is. Without a witness, the universe is a story without a reader, a song without a listener. With us, it becomes a known, felt, and meaningful reality. We are not an accident or an afterthought. We are the universe's way of waking up. The physicist Freeman Dyson imagined a future where intelligent life might exist as vast, conscious clouds of energy, thinking and remembering for eternity in a cold, dark universe. It's a beautiful thought, that even in the final, dying embers of the cosmos, the spark of consciousness could persist. That the universe, having once woken up, would find a way to never fall back into an unthinking, unwitnessed sleep. So, the next time you look up at the stars, don't feel small. Feel connected. You are not just looking at the universe. You are the universe looking back at itself. You are a censor, a poet, and a philosopher for the cosmos. You are a temporary, fragile, and precious island of meaning in the great, silent sea of existence. And that, in its own quiet way, is a purpose as vast as the universe itself.